Welcome to the Tired Thinker, where the stars do not simply shine, but whisper, and the universe stretches in all directions at once, refusing to explain itself. Tonight's curiosity belongs to the cosmos, to riddles suspended in vacuum, to questions older than planets, to signals that may or may not be calling back. Out there in the dark, mysteries hang like lanterns, galaxies moving too fast, as if something invisible holds them. Black holes that devour light, yet reveal structure in the silence they leave behind. Signals from distant stars that flicker just strangely enough to make us wonder if we're being noticed. Each one asks, if space is endless, what exactly does it expand into? If life began here, why shouldn't it begin elsewhere? And if the universe had a beginning, was there a before? These are not puzzles to be solved tonight, but constellations to drift inside. Let the mind loosen. Let the dark feel vast, but gentle. Let curiosity be a flashlight, not a compass. So tell me, where on earth are you listening from tonight? Which horizon is holding your sky? And if these mysteries spark something in you, a quiet awe, a soft hum of could it be? I'd be grateful if you liked or subscribed, so more wanderers can drift into these stellar uncertainties. Now, take a breath, look up. Let's begin. We listen to space with antennas. They look simple from a distance, metal frames pointed at the sky, silent and still. But those antennas are not watching. They are listening. Not for words, not for music. They are listening for patterns in noise, the quiet hiss of the universe. And in that noise, sometimes there are signals we cannot explain. A radio telescope collects electromagnetic waves, the same kind used by radios and cell phones. These waves can tell us where stars are, how galaxies move, and what the early universe sounded like after the Big Bang. Most of the signals we pick up are natural. Pulsars send out steady pulses. The sun crackles with solar activity. Jupiter sends bursts of radio noise. These things follow patterns we understand. They can be measured. They can be predicted. But sometimes something else comes through. In 1967, a graduate student named Jocelyn Bell was watching the data charted on long rolls of paper. The telescope showed a repeating signal, pulsing every 1.3 seconds. It was too regular, too exact, not like a star, not like a planet. It was as precise as a clock. For a moment, the team joked that it might be a message. They labeled it LGM-1. LGM stood for Little Green Men, not because they believed in aliens, but because the pattern was unfamiliar. It was worth asking what could make something so orderly. Later, they learned the signal came from a pulsar, the collapsed core of a massive star spinning fast. It was a natural object, but one we had never seen before. A mystery, then explained. But only after the listening came the wondering, and only after the wondering came the understanding. Not every mystery has followed that path. In 1977, another signal appeared. It came from a radio telescope in Ohio, part of a project called SETI, which searches for signs of life beyond Earth. The signal lasted 72 seconds. It had the features of something artificial, not random, not noise. It came from a specific point in the sky near the constellation Sagittarius. The volunteer who reviewed the printout saw the spike of data and circled it with a pen. Next to it, he wrote one word: wow. That is still the name of the signal today. We have never heard it again, not once. We pointed many telescopes back to that part of the sky. We waited. Nothing returned. No repeat, no pattern. A single, one-time event. There are explanations. A satellite we did not log, a natural cosmic burst, a reflection from space junk. a signal from a planet-sized gas cloud. None of these have been proven. None fit quite right. The wow signal remains something we picked up and cannot yet explain. When we talk about voices in the static, we are not talking only about the wow signal. We are talking about a category of events, signals that appear once, signals that do not match known stars, galaxies, pulsars, or planets. They are short, they are sharp, they are specific. They arrive, they vanish. One example is FRBs, fast radio bursts. These are bursts of radio energy that last a fraction of a second. Most come only once. They are powerful. Some release more energy in that instant than the sun releases in days. We can measure their strength. We can measure how far they traveled, but we do not know what makes them. Some FRBs repeat, though irregularly. This makes them useful. When they repeat, we can track them. One repeating FRB came from a galaxy about 3 billion light-years away. It sent signals at intervals that looked nearly patterned, then stopped, then started again. We could point our instruments at it. We could watch it. This gave us time to recognize it likely came from a magnetar, a neutron star with a powerful magnetic field, but the exact mechanism of the burst is still not known. There are FRBs that do not repeat. We have one shot, one burst, one signal, no second chance. This is like hearing a knock in the middle of the night, walking outside and seeing no one there. When people talk about extraterrestrial intelligence, these are often the events they refer to. But scientists do not label a signal alien unless there is no natural explanation left. It is more cautious to assume nature has surprises we have not cataloged than to claim the source is intentional communication. Still, the question remains, if another civilization were sending a signal, how would we know? A natural signal tends to drift. It spreads. It changes slightly in frequency. But an artificial signal tends to be narrower, cleaner, more stable. Some of the unexplained signals we found are narrow. That alone does not prove anything, but it keeps the door open. Imagine you sit in a quiet room with a radio on low volume. You hear static, nothing unusual. Then, faintly, you hear 3 tones. Not music, not speech, just tones. They play, they stop, you wait, they return. You do not recognize them. You check the dial. No known station matches that frequency. You do not know whether someone meant to send them, but something did. Space listening can feel like that. There is a difference between searching for meaning and listening for structure. Meaning suggests language. Structure suggests intention. When a signal does not match the patterns of stars, planets, pulsars, or cosmic plasma, we say it is structured. That means it is worth attention. If a civilization wanted to reach others across space, radio waves would make sense. They travel far. They move at the speed of light. They pass through dust and gas. They are simple to generate. We already use them. If we send a message into space, we send it in radio. So when we hear something structured, the question forms whether we want it to or not. Is someone trying to speak? But the universe is old, billions of years old. Civilizations may rise and fall before we ever hear them. A signal could arrive centuries after the one who sent it vanished. If we sent a reply, it might take thousands of years to return to its source. Communication on this scale is not conversation. It is more like leaving notes in bottles and releasing them into a tide. We listen because listening is the first part of understanding. When we tune our antennas toward the sky, we are not expecting a language we can translate easily. We are listening for consistency, for repeatability, for something that stands apart from noise. The static is not empty. It holds the background radiation of the early universe, the rotation of galaxies, the pulse of dying stars, the quiet shimmer of dust clouds. It holds memory. When something unfamiliar enters that field of noise, it stands out the way a single footstep stands out in fresh snow. Most of the universe is silence, not silence of absence, but silence of distance. Space does not refuse to speak. It speaks at scales that are slow and wide and patient. Our job is to learn how to listen without rushing to name what we hear. Sometimes a signal will resolve into a known pattern, like the pulsar did. Sometimes it will remain a single event, like the wow signal. Sometimes it will return, like the repeating FRBs. Sometimes we will watch for years, with nothing new to show for it. We listen anyway. When we talk about galaxies, we talk about groups of stars held together by gravity. They develop over time. They form from clouds of gas that collapse and spin. The first galaxies needed time to grow. They needed matter to gather, stars to ignite, and gravity to hold it all in place. According to the timeline we work with, the universe is about 13.8 billion years old. The earliest galaxies should be younger than that because they formed within the universe. They cannot be older than the space that contains them. But there are galaxies that make us pause. Some appear so old, so mature, and so massive that they do not fit the timeline. Their stars look ancient. Their structure looks settled. They do not show signs of early chaos. They look finished, not forming. The question that follows is simple. How did they have enough time to become so complete? This is not guesswork. We have telescopes that can look so far away that we are looking back in time. Light takes time to travel. When we look at a distant galaxy, we are seeing it as it was billions of years ago. The farther away the object, the older the light. When scientists found galaxies in the deep field images of the James Webb Space Telescope, they expected to see small, young, rough galaxies. They expected shapes that were still gathering stars. Instead, they found galaxies that were large, dense, bright, and old. Their stars seemed aged. Their mass was too high for how early they appeared in cosmic history. In plain terms, they looked like galaxies that should have taken billions of years to form. But they were seen at a time only a few 100 million years after the Big Bang. Imagine you wake up one morning and find a full-grown oak tree in your yard. Not a sapling, not a young tree. A massive tree with thick branches, rings in the wood, and roots deep into the ground. You know oak trees do not grow overnight. They take decades. So you ask, how did this one get here? Did it grow faster than every oak we know? Did it appear fully formed? Or does something about how oak trees grow need to be reconsidered? This is the position astronomers are in. There is one example often discussed, a galaxy labeled Jade's GS Z130. It appears only 320 million years after the Big Bang. That sounds like a long time, but in cosmic terms, it is early morning on the first day. At that point, the universe was still hot, dense, and settling. Stars were only beginning to form in meaningful numbers. Galaxies should have been small clumps, uneven and messy. Yet this galaxy shows a level of development that does not match the expected timeline. This does not mean the galaxy is older than the universe. It means something about our understanding of galaxy formation might not be complete. The rules may not be wrong, but the timing may be off. There are several possibilities. One explanation is that stars formed faster than we thought they could. Gas could have collapsed more quickly. Cooling might have been more efficient. If early stars formed in large numbers at once, galaxies could grow faster than expected. But this would require conditions we have not yet proven. Another possibility is that dark matter played a stronger role than we realized. Dark matter does not interact with light. We cannot see it, but it has gravity. If more dark matter clumped early, it could create deeper gravitational wells. Gas would fall into these wells faster. That could speed up galaxy formation. There is also the chance that we are measuring age in a way that needs adjustment. We infer a galaxy's age by the light its stars emit. Older stars emit different spectra than young ones. But if early stars form differently, larger, hotter, brighter, that could change how we interpret their age. A simpler way to say it, we may not yet understand what early stars looked like. Consider a scenario. You walk into a room and see a person with gray hair. You assume they are older. But imagine a world where hair color changed for reasons other than age. You would misjudge their age without knowing the rule had changed. Something like that may be happening with early galaxies. There is even a more unsettling possibility. The timeline of the universe may not be as clean as we think. Our estimate of 13.8 billion years is based on how the universe expands. If expansion behaved differently at different times, the clock we use to measure age could have calibration issues. That does not mean the universe is younger or older in a dramatic sense, but small adjustments could shift the window of possible galaxy growth. Scientists do not jump to this answer first. Changing the timeline of the universe is a major step. It requires strong evidence, not only unusual observations. The more conservative approach is to assume something about early matter or early star formation acted differently. But even the conservative explanation asks us to rethink something we thought we understood. A galaxy that shouldn't exist forces the mind to slow down. It forces us to consider that models are not final. They are tools. They are useful because they work well most of the time. But when something does not fit the model, we do not ignore the object. We adjust the model. We have been through this before. When pulsars were first discovered, they were regular and fast. We did not know what could produce such precision. We labeled the first signal LGM1 for little green men. Then we learned they were neutron stars, and the model expanded. When quasars were first found, they were bright in ways that did not match stars or galaxies. For a while, they were simply unexplained. Then, as we learned more about black holes, we understood that matter swirling into a black hole could release huge amounts of energy. The galaxy that shouldn't exist is part of that tradition. It is a signal, not of aliens, not of something impossible, but of something we do not yet know how to describe. If a galaxy can form faster than the timeline allows, then the early universe was more efficient at building structure than we assumed. If the universe built galaxies more efficiently, then the early cosmos was not quiet and slow, but active and quick. This picture is different from the one we teach now. When we listen to space, we often imagine silence and emptiness. But the early universe may have been crowded with energy, collapse, ignition, and growth. A place of rapid assembly, not slow evolution. The galaxies that should not exist may not be mistakes. They may be reminders that the universe is not finished showing us how it works. When we talk about galaxies, we talk about groups of stars held together by gravity. They develop over time. They form from clouds of gas that collapse and spin. The first galaxies needed time to grow. They needed matter to gather, stars to ignite, and gravity to hold it all in place. According to the timeline we work with, the universe is about 13.8 billion years old. The earliest galaxies should be younger than that because they formed within the universe. They cannot be older than the space that contains them. But there are galaxies that make us pause. Some appear so old, so mature, and so massive that they do not fit the timeline. Their stars look ancient. Their structure looks settled. They do not show signs of early chaos. They look finished, not forming. The question that follows is simple. How did they have enough time to become so complete? This is not guesswork. We have telescopes that can look so far away that we are looking back in time. Light takes time to travel. When we look at a distant galaxy, we are seeing it as it was billions of years ago. The farther away the object, the older the light. When scientists found galaxies in the deep field images of the James Webb Space Telescope, they expected to see small, young, rough galaxies. They expected shapes that were still gathering stars. Instead, they found galaxies that were large, dense, bright, and old. Their stars seemed aged. Their mass was too high for how early they appeared in cosmic history. In plain terms, they looked like galaxies that should have taken billions of years to form. But they were seen at a time only a few 100 million years after the Big Bang. Imagine you wake up one morning and find a full-grown oak tree in your yard. Not a sapling, not a young tree, a massive tree with thick branches, rings in the wood, and roots deep into the ground. You know oak trees do not grow overnight. They take decades. So you ask, how did this one get here? Did it grow faster than every oak we know? Did it appear fully formed? Or does something about how oak trees grow need to be reconsidered? This is the position astronomers are in. There is one example often discussed, a galaxy labeled Jade's GS Z130. It appears only 320 million years after the Big Bang. That sounds like a long time, but in cosmic terms, it is early morning on the first day. At that point, the universe was still hot, dense, and settling. Stars were only beginning to form in meaningful numbers. Galaxies should have been small clumps, uneven and messy. Yet this galaxy shows a level of development that does not match the expected timeline. This does not mean the galaxy is older than the universe. It means something about our understanding of galaxy formation might not be complete. The rules may not be wrong, but the timing may be off. There are several possibilities. One explanation is that stars formed faster than we thought they could. Gas could have collapsed more quickly. Cooling might have been more efficient. If early stars formed in large numbers at once, galaxies could grow faster than expected. But this would require conditions we have not yet proven. Another possibility is that dark matter played a stronger role than we realized. Dark matter does not interact with light. We cannot see it, but it has gravity. If more dark matter clumped early, it could create deeper gravitational wells. Gas would fall into these wells faster. That could speed up galaxy formation. There's also the chance that we are measuring age in a way that needs adjustment. We infer a galaxy's age by the light its stars emit. Older stars emit different spectra than young ones. But if early stars form differently, larger, hotter, brighter, that could change how we interpret their age. A simpler way to say it, we may not yet understand what early stars looked like. Consider a scenario. You walk into a room and see a person with gray hair. You assume they are older. But imagine a world where hair color changed for reasons other than age. You would misjudge their age without knowing the rule had changed. Something like that may be happening with early galaxies. There is even a more unsettling possibility. The timeline of the universe may not be as clean as we think. Our estimate of 13.8 billion years is based on how the universe expands. If expansion behaved differently at different times, the clock we use to measure age could have calibration issues. That does not mean the universe is younger or older in a dramatic sense. But small adjustments could shift the window of possible galaxy growth. Scientists do not jump to this answer first. Changing the timeline of the universe is a major step. It requires strong evidence, not only unusual observations. The more conservative approach is to assume something about early matter or early star formation acted differently. But even the conservative explanation asks us to rethink something we thought we understood. A galaxy that shouldn't exist forces the mind to slow down. It forces us to consider that models are not final. They are tools. They are useful because they work well most of the time. But when something does not fit the model, we do not ignore the object. We adjust the model. We have been through this before. When pulsars were first discovered, they were regular and fast. We did not know what could produce such precision. We labeled the first signal LGM-1 for little green men. Then we learned they were neutron stars, and the model expanded. When quasars were first found, they were bright in ways that did not match stars or galaxies. For a while, they were simply unexplained. Then, as we learned more about black holes, we understood that matter swirling into a black hole could release huge amounts of energy. The galaxy that shouldn't exist is part of that tradition. It is a signal, not of aliens, not of something impossible, but of something we do not yet know how to describe. If a galaxy can form faster than the timeline allows, then the early universe was more efficient at building structure than we assumed. If the universe built galaxies more efficiently, then the early cosmos was not quiet and slow, but active and quick. This picture is different from the one we teach now. When we listen to space, we often imagine silence and emptiness. But the early universe may have been crowded with energy, collapse, ignition, and growth. A place of rapid assembly, not slow evolution. The galaxies that should not exist may not be mistakes. They may be reminders that the universe is not finished showing us how it works. When we look at a galaxy, we see stars arranged in spirals or clustered in spheres. We see glowing gas, dust lanes, and sometimes bright cores. It is natural to assume that what we see is what is there. Our eyes take in the light, and the mind builds the rest. But the visible parts of a galaxy are only a small fraction of its mass. The light we see does not account for the way galaxies behave. Something else holds them together. Gravity keeps stars in orbit around the center of a galaxy. The stars move fast, yet they do not fly away into space. If we only count the visible matter, gravity seems too weak to hold the galaxy together. The mass we can see does not match the motion we observe. To make the math work, there must be more matter than what emits light. That unseen mass is what we call dark matter. Dark matter is not dark in the sense of shadow. It does not absorb light. It does not reflect light. It does not emit light. It does not interact with electromagnetic waves. Light passes straight through it. Because of this, we cannot see dark matter by observing light. We detect it by its influence. We watch the way galaxies rotate. We watch the way clusters of galaxies bend light through gravitational lensing. The presence of dark matter shows up in motion and shape, not brightness. Imagine spinning a stone on a string. The stone moves in a circle because the string pulls it inward. Now imagine removing the string. The stone flies away. In a galaxy, stars are the stones. Gravity is the string. Based on the amount of visible matter, the gravitational pull should be weak. The stars should drift outward, but they do not. They stay in place because there is more mass pulling inward than what we can see. That added mass is dark matter. Some galaxies show this effect more clearly than others. Spiral galaxies, in particular, rotate with nearly constant speed from their center to their edges. If only visible matter were present, the stars at the edges would rotate slower than the stars near the center. But this is not what we observe. The rotation curves remain flat. This means the mass distribution extends farther than the visible stars and gas. The galaxy is wrapped in a halo of dark matter. The halo is not a ring or a shell. It is a sphere of unseen mass surrounding the galaxy. It holds everything in place. The stars, gas, planets, nebulae, and any life that exists all move inside this invisible structure. Without it, the shapes of galaxies would not hold. They would spread out over time. Dark matter does not clump into stars. It does not collapse under its own gravity the way normal matter does. It spreads in a diffuse form. It forms frameworks, like scaffolding, upon which galaxies hang. In the early universe, dark matter pulled gas toward itself. Gas cooled and collapsed to form stars. In that sense, dark matter guided the formation of galaxies. It acted as the architecture of cosmic structure. We live inside a dark matter halo ourselves. The Milky Way is surrounded by it. We do not feel it directly. We do not see its presence with our eyes or hands. But the solar system, Earth, and every atom here sits inside that influence. If dark matter is so important, it is fair to ask what it is made of. The honest answer is that we do not know. There are possibilities. One idea is that dark matter could be made of particles that do not interact with normal matter except through gravity. These particles would be unlike protons, electrons, or neutrons. They would not combine to form atoms. They would pass through ordinary matter without stopping. We could be moving through dark matter every day without noticing. There have been attempts to detect dark matter particles directly. Experiments place sensitive detectors deep underground to shield them from noise. The hope is that a dark matter particle might collide with an atomic nucleus and leave a trace. So far, results are uncertain. Some experiments report signals, others do not. The search continues. Another possibility is that our understanding of gravity is incomplete. Instead of adding unseen matter, perhaps the rules of gravity behave differently at large scales. This idea has led to modified gravity theories. These models try to explain galaxy rotation without dark matter, but they struggle to explain other observations, such as the way galaxy clusters bend light. Dark matter remains the more consistent explanation across many different phenomena. Consider a simple scenario. You are sitting in a park, watching leaves swirl in the wind. You cannot see the wind, but you see its effects. The motion of the leaves, the sway of branches, and the shift of the grass all show that something invisible is present. Dark matter behaves in a similar way. We infer its presence through motion. We see the way galaxies behave, and we know something unseen provides structure. Galaxy clusters offer a clear demonstration. A galaxy cluster contains many galaxies grouped together. When we measure their motion, we find they move too fast to stay bound by the visible mass. Something else must provide the gravity that holds the cluster together. Then we use gravitational lensing to measure the mass. Light from distant galaxies bends as it passes through the cluster. The bending tells us how much mass is there. The mass we detect is far greater than the mass we can see. Once again, the difference is dark matter. The concept of something unseen shaping the universe can feel abstract. But we live with unseen forces every day. Gravity itself is invisible. We believe in it not because we see it, but because we experience its effect. Dark matter is similar. Its presence shows in structure, motion, and stability. The name dark matter sounds mysterious, but it is plain in meaning. It is matter we cannot detect with light. The term does not imply intent or personality. It simply notes that this matter is hidden from direct observation by the methods we use to see the universe. The universe contains what we can see and what we cannot see. Both shape the world we live in. We exist in a galaxy held together by something we cannot touch. The stars move within an unseen frame. The gentle grip that binds them is steady. It has worked for billions of years. It works now. We continue to study it, not to prove a story, but to understand what is actually there. There are planets that reflect light, planets that glow in infrared heat, and planets with bright clouds. When we look at worlds in our own solar system, we see variety in color and texture. Earth reflects blues and whites. Mars reflects rusty red. Jupiter reflects bands of tan and cream. Even the darker worlds still return some light back towards space. They are dim, but not silent. But there are planets outside our solar system that do something different. Some absorb almost all the light that reaches them. They reflect so little that they appear black. One example is a planet called TREES 2b. It orbits a star not far from the constellation Draco. When telescopes measure how much light it reflects, the number comes back almost zero. It returns less light than coal, less than black paint, less than the surface of a new asphalt road under a moonless sky. The planet is large, about the size of Jupiter. It is close to its star. It receives strong light, but instead of shining with reflected brightness, it seems to swallow the light whole. It is a world where light enters and does not come back. To understand how this happens, it helps to consider how reflection works. When light hits an object, some wavelengths bounce off and reach our eyes or instruments. That is reflection. But if the surface absorbs light instead of reflecting it, the light becomes heat or is transformed inside the material. A black surface absorbs more light than a white one. This is why a black shirt feels warmer in the sun. On Earth, the darkest materials still reflect a small amount of light. There is always some return. But TREES 2b reflects almost none. The reflectivity known as albedo is extremely low. This suggests that its atmosphere or surface contains material that absorbs nearly every photon that touches it. The planet is likely a gas giant. That means it does not have a solid surface like Earth. It is made of gases held by gravity with high pressure near the center. The atmosphere could contain sodium, potassium, or other elements that absorb light, but even those do not fully explain how dark it is. There are models that suggest the atmosphere might contain titanium oxide or vanadium oxide. These compounds can absorb large amounts of light, but for them to stay in the atmosphere, the temperature must be extremely high. TREES 2b is close to its star, so it could be hot enough for such compounds to remain in gaseous form. When we measure light from a planet, we are not looking directly at the planet itself. We detect the small dip in starlight when the planet passes in front of the star. Then we measure how the light changes when the planet passes behind the star. By comparing the two, we estimate how much light the planet adds to what we see. In this case, the added light is nearly zero. The planet contributes almost no reflection. Because the planet absorbs so much energy, it must emit some of it as heat. Infrared observations show that the planet glows faintly in heat radiation. It does not glow in the visible spectrum. To the eye, it would be a black sphere hanging against the even darker background of space. If someone were close enough to see it, they might not be able to distinguish its shape except when it eclipses the star. The horizon would not be a line against a sky. It would be the same shade as everything else. If you stood on a gas giant, you would not stand on a solid surface. You would descend into thicker layers of gas and pressure. But if you could float inside its atmosphere, you would find yourself in a place with no natural day or night. Light would not travel far. It would be like being inside a dense smoke cloud where beams fade before reaching anything. This planet raises a more general question. How many worlds like this exist? When we look at space, we tend to focus on what shines. Bright stars, glowing nebulae, galaxies lit by billions of suns. But space is also full of objects that do not reflect or emit light. These objects are harder to detect. They require indirect observation. If TRIES-2b were not orbiting a bright star in a way that crosses our view, we might never know it exists. A planet that absorbs light can hide in plain sight. There could be many mere worlds like it that we have not detected because they do not return any signal. We rely on light to show us where things are. When something refuses to reflect light, it blends into the background. To think through the scale of this, imagine walking through a large room with the lights off. You shine a flashlight. You see what the light strikes and reflects from. But if an object absorbs all the light, you will not know it is there until you touch it. The universe works in a similar way. Sometimes we detect objects not through their light, but through their gravity. They pull on other stars, and we measure the pull. TRIES-2b shows that some planets have atmospheres, arranged in ways we did not expect. It expands our sense of what a planet can be. Before this discovery, we assumed that most planets would reflect some recognizable amount of light. Now we know reflection is not a given. Light can enter a world and vanish from sight. This does not mean the planet is lifeless or alive. Darkness alone does not tell us that. It tells us that conditions are extreme. It tells us that temperatures and atmospheric makeup combine to erase visible light. Anything existing in such conditions would need to survive in heat, pressure, and lack of sunlight. The name, the planet made of night, does not describe its composition. It describes its appearance. Night is not a substance. It is the absence of light. This planet is not made of night. It creates night by refusing to return the light that touches it. If we could travel there, we would not see a landscape. We would not see a horizon. We would be surrounded by blackness that is not empty, but full. It would be a darkness that is occupied, dense, and warm. The star would still shine, but the world would not answer with reflection. The light would fall and not return. At the center of our galaxy sits a black hole. It does not shine. It does not glow. It does not signal its position with any light we can see. Yet everything around it moves with its pull. Stars orbit it. Clouds of gas spiral near it. The structure of the Milky Way depends on it. This presence does not announce itself, and yet it shapes the entire galaxy. A black hole forms when enough mass collapses into a small space. The gravity becomes so strong that not even light can escape. When we talk about the black hole at the center of the Milky Way, we talk about something far larger than the black holes formed by dying stars. The one at our center has a mass about 4 million times that of the Sun. It is called Sagittarius A star. It is not the only supermassive black hole in the universe. Most galaxies have one at their center. Their size varies, but their influence is the same. They hold the structure of their galaxies in place. When we describe a black hole, we talk about the event horizon. The event horizon is the boundary around the black hole. Nothing that crosses this boundary returns. Not matter, not light, We cannot see inside. We do not know what happens beyond that line. The physics we use to describe the universe breaks down there. We have equations that describe gravity and equations that describe quantum mechanics, but they do not agree inside a black hole. The center, called the singularity, is a point where density becomes something we do not know how to describe. It is not a place, but an idea that marks the limit of our understanding. Even though we cannot see a black hole, we can observe the way it affects the matter around it. When gas gets close, it heats up from friction as it swirls inward. That gas can emit X-rays and radio waves. This is how we detect Sagittarius A star. We do not see the black hole. We see the space around it reacting. The quiet nature of a black hole can be misleading. We might imagine a violent pull, like water draining. But in most circumstances, a black hole does not actively pull objects in. If the sun were replaced by a black hole of equal mass, Earth's orbit would remain the same. The daylight would vanish, but the orbit would stay. Gravity depends on mass, not on what form that mass takes. A black hole only draws material inward when something passes close enough to cross the event horizon. The image of black holes as cosmic vacuum cleaners is not accurate. They do not chase matter, they wait. At the center of our galaxy, stars move in tight elliptical orbits. These orbits tell us the black hole is there. We track stars like S2, which orbits once every 16 years. Its path curves fast when it nears Sagittarius A star, then slows when it moves away. From these motions, we calculate the mass of the black hole. The measurements are consistent. Something dense and massive sits at the center. The idea of a quiet center is not only a physical description, it also has a visual counterpart. When we look at the image produced by the Event Horizon Telescope in 2022, we see a ring of glowing gas around a dark core. The glow is not from the black hole, it is from the matter heating as it spirals near the event horizon. The center is not simply dark, it is silent in a way that feels complete. There is no texture, no reflection, no outline. It is space emptied of the familiar relationship between light and matter. Understanding this requires letting go of the idea that darkness is nothing. The darkness of a black hole is not absence. It is a region from which information does not return. That is different from empty space. In empty space, light can travel. Inside a black hole's boundary, light cannot. It may help to think about it like this. Imagine standing on a cliff overlooking the ocean at night. The sea is black. You cannot see its movement from where you stand. But if a wave hits rock, you hear it. If a moon reflects, you see a shimmer. The ocean is dark, but not silent. A black hole is different. There is no shimmer. There is no returning sound. No evidence of what enters. We know that black holes can grow. They grow when stars, gas, or even other black holes fall in. They grow slowly most of the time. But sometimes a black hole becomes active. Gas collects in a disk and spirals inward. When this happens, the region around the black hole flares with energy. Some galaxies show bright beams extending thousands of light years. These beams, called jets, are not the black hole itself, but the result of magnetic fields channeling energy away from the accretion disk. The black hole remains quiet beneath the activity. The energy is the environment reacting to the gravitational well. In our galaxy, Sagittarius A star is mostly quiet. It is not consuming large amounts of matter right now. We observe occasional flares, small bursts of X-rays, but nothing extreme. It is like a calm fire pit with embers, not an active blaze. If we imagine traveling toward the center of the galaxy, we would see stars grow dense. The night sky would brighten, not darken. The center of the Milky Way is crowded with stars, dust, and gas, but past a point, the brightness would fade and the temperature would rise. As we approached the event horizon, light from behind us would stretch and shift. Time would feel different depending on where you are standing. Clocks near the event horizon tick slower compared to clocks far away. This is not metaphor. It is gravitational time dilation, a real effect predicted by general relativity. If someone fell toward a black hole, an observer far away would see them slow as they approach the event horizon. Their image would stretch and fade. The person falling would feel no change crossing the boundary. They would continue until reaching a region where our understanding stops. This difference between what is seen and what is experienced is part of the quiet. The black hole does not signal its presence with eruption or roar. It bends time and space without sound. At the center of our galaxy, this quiet presence continues. It holds everything in orbit, steady and constant, shaping the paths of stars that shine while it remains unseen. The universe carries memory. Not memory in the way a mind remembers, but memory in the form of signals that remain from events long past. One of these signals is the cosmic microwave background. It is a faint radiation spread across the sky in every direction. No matter where you look, the same soft glow appears. It is the afterglow of the Big Bang, stretched and cooled over billions of years as the universe expanded. The cosmic microwave background, often called the CMB, looks uniform at first. But when scientists measure it with sensitive instruments, they see tiny differences in temperature. These differences are small, only a fraction of a degree. They show that the early universe was not perfectly smooth. It had denser regions and thinner regions. Over time, gravity turned the dense regions into galaxies and stars. The CMB is like a photograph taken when the universe was just 380,000 years old. It shows the seeds of everything we see today. The first Big Bang is our standard origin story. Space, time, matter, and energy all began in a state of high temperature and density. Then the universe expanded and cooled. That is the model that fits most observations. But when we examine the CMB with more precision, some patterns do not line up neatly. There are regions slightly warmer or cooler than expected. There are alignments and asymmetries that are hard to explain with simple random variation. This raises a question that is not easy to answer. Could something have happened before the Big Bang? One idea suggests that the universe might have gone through more than one cycle of expansion. In this view, the Big Bang is not the beginning, but one event in a longer sequence. This concept appears in models like the cyclical universe and the ekpyrotic universe. These models propose that the universe expands, slows, contracts, and then expands again. If this is true, the Big Bang we talk about may not be the first. It may be one of many. If there was a universe before ours, or a phase before the expansion we know, is there any trace of it left? One place to look would be the cosmic microwave background. The CMB carries information from the earliest visible moment. If something influenced the universe before that moment, its fingerprint might show up as a subtle irregularity. Some researchers have suggested that certain circular patterns in the CMB could be traces of events that happened before the expansion. These patterns are sometimes described as low-variance circles. The idea is that if black holes collided in a previous universe, their energy could ripple into the next cycle. The ripples might show up as faint rings in the CMB. This idea is not universally accepted. It is debated, but it shows how scientists work with signals that are faint and ambiguous. Another approach focuses on inflation. Inflation is the theory that the universe expanded faster than the speed of light in the first fraction of a second after the Big Bang. This rapid expansion smoothed out the universe. It explains why the CMB looks almost uniform, but inflation requires an energy field to drive it. The nature of that field is still unknown. Some physicists suggest that the same field could be part of an earlier event. If inflation did not start from zero, but from conditions carried over from something before, the CMB might reflect that. To make this easier to picture, imagine you are looking at ripples on the surface of a pond. The ripples come from pebbles dropped in the water. If a wave from an earlier pebble still lingers when you drop a second pebble, the new ripples will overlap with the old ones. You might not see the original ripple clearly, but you see a distortion in the pattern. The CMB could be like the pond. The irregularities could be the overlapping of cycles. The idea of a second Big Bang does not refer to an explosion happening again in time as we understand it. It refers to the start of another expansion phase. It might follow a contraction, or it might come from a transition between different states of space. The language is limited because we do not have everyday experience with the scale or conditions involved. There is another path to the same question. Quantum fluctuations are small variations in energy that occur even in empty space. During inflation, these fluctuations stretched to enormous scales. They became the seeds of galaxies. If there were fluctuations before inflation, they could leave marks on the CMB as well. Again, we would see them as slight temperature differences. The CMB has been mapped many times. The Comet satellite gave us the first detailed map, then WMAP improved it. The Planck satellite gave the most precise map to date. Each map confirms that the CMB is not perfectly even. Each map also confirms certain irregularities that are difficult to classify as random. One example is known as the cold spot. It is a region larger and cooler than expected. There are theories that it could be caused by a supervoid, a large empty region in space, but there are also ideas that it could be a remnant of an earlier universe. Both explanations remain on the table. The presence of unexplained features does not prove a second Big Bang. It shows that our current model is not complete. The CMB is a record of the early universe, but we interpret it through the models we build. If the models change, the interpretation changes. This is a pattern in science. We observe first. We explain second. The explanation adjusts as new information arrives. When radio waves from pulsars were first detected, the signals were so regular that some wondered whether they were artificial. Later, we understood they were rotating neutron stars. The mystery did not disappear. It became part of a larger understanding. The CMB remains one of the strongest sources of information about cosmic origins. It tells us where we came from. It may also hint at what came before. If there was a phase before the Big Bang, its shadow may be written in the background radiation that surrounds us, quiet and even, filling every direction, waiting for interpretation. ... Most stars belong to galaxies. They orbit within large systems held together by gravity. Our Sun is one of many stars in the Milky Way, circling the center over hundreds of millions of years. The idea of a star without a galaxy may seem unusual because we often imagine stars as part of structured groups. But not all stars stay where they formed. Some drift through space alone. These are called rogue stars. A rogue star does not orbit a galactic center. It moves through space without a stable home. It may have once belonged to a galaxy, then been forced out. It may have formed in an environment where galaxies collided and tore material loose. It may be moving so fast that it will leave any galaxy it enters. But however it happened, the result is the same: a star traveling without the framework of a stable stellar neighborhood. One way a star becomes a rogue star is through gravitational interactions. Galaxies are not still. They collide, merge, and sometimes tear material from each other. During these events, stars can be slingshotted outward. When two galaxies pass near each other, their gravitational fields interact. Stars near the edges can be caught in the shifting pull and thrown away. Once they gain enough speed, they leave the galaxy entirely. Another way involves black holes. If a star orbits near a supermassive black hole at the center of a galaxy, it might follow a close path. If a second star crosses that path, the interaction between the two stars and the black hole can fling one star outward. The star that gets thrown receives a burst of velocity. It becomes what is called a hypervelocity star. Some of these stars move fast enough to escape the galaxy and continue into intergalactic space. When we say a star is wandering, we are describing motion across vast distances. A rogue star might travel through space where the nearest star is millions of light years away. There is no warm glow of a nearby cluster. There are no bright nebula. The star shines into darkness. It produces light, but the light travels without reflecting from nearby dust or planets. To any observer near that star, the night sky would be nearly empty. There would be no familiar band of the Milky Way. The sky would be black, with few points of light. If a planet orbited such a star, it would see a different kind of night. On Earth, we see stars because we live within a galaxy rich in starlight. A planet around a rogue star would look into deep space. The nearest galaxy might appear as a faint, hazy smudge. There would be no bright constellations. Any life there would grow up with a different idea of the universe. They might believe themselves isolated, surrounded by emptiness, with no clear evidence of other suns. The motion of a rogue star is slow on human timescales. Even a hypervelocity star, traveling at millions of miles per hour, takes millions of years to cover the gap between galaxies. The star does not notice its isolation. It does not need a galaxy to fuel its energy. It continues fusion at its core. It continues to shine. The difference is in what surrounds it. We detect rogue stars by measuring their velocity and direction. A normal star in a galaxy follows a shared rotational pattern. When a star moves in a way that does not match that pattern, we measure its speed. If the speed is high enough, and if the direction is outward rather than circular, we identify it as leaving the galaxy. Some hypervelocity stars move so fast that they exceed the galaxy's escape velocity. Once they cross the boundary, they will not return. There are also stars that formed outside galaxies. During the earliest stages of the universe, matter was not evenly distributed. Some regions had higher density, some lower. If enough gas gathered in a low-density region, it could form stars without ever joining a galaxy. These stars are rare, but not impossible. They would be isolated from the beginning. Rogue stars help us understand galaxies by highlighting the forces at work. When a galaxy interacts with another, the motion of rogue stars reveals the strength and direction of gravitational pulls. Studying these stars can show how galaxies merge. It can also show the influence of dark matter. Dark matter creates the gravitational scaffolding that holds galaxies together. When we see how stars behave at the edges, we gain information about mass we cannot see. A rogue star also reminds us that space is not a smooth expanse with stars placed at even distances. It is uneven. It has dense regions and empty regions. The universe is full of structure and void. A rogue star travels through that structure without belonging to any of it. If we imagine traveling alongside such a star, the journey would be long and quiet. There would be no nearby galaxies filling the sky. There would be no neighbors. The star would shine into darkness, and the darkness would not answer. The only constant would be the star itself. Yet this isolation is not a sign of disorder. It is one outcome of the universe's natural movement. Galaxies collide, stars interact, gravity gives and takes. A star without a galaxy is not lost. It is simply elsewhere, carrying its own light with it, moving in a direction shaped by events that may have happened billions of years earlier. The wandering suns do not call attention to themselves. We find them when we look closely at the motion of stars and ask why some travel faster or farther than expected. When we track them, we see the trace of past collisions written in their paths. These quiet travelers show that the universe is dynamic. Nothing stays fixed forever. The places where stars form are not always the places where they remain. When we think of oceans, we picture Earth. We picture waves, currents, open water, and shorelines. But Earth may not be the only place with oceans. Some of the most promising places to find life in our solar system do not look like Earth at all. They are frozen worlds. Their surfaces are ice, hard and bright. But beneath the ice, there may be deep oceans of liquid water. These are internal oceans, sealed away from sunlight. They remain liquid because of heat from inside the moon. The most well-known examples are Europa, one of Jupiter's moons, and Enceladus, one of Saturn's. Europa is covered in a shell of ice. When spacecraft have photographed it, they show a smooth surface marked by long cracks. The surface is not heavily cratered, which means it is young. Something renews it over time. Beneath the ice, measurements of gravity and movement suggest a global ocean. This ocean could be deeper than any on Earth. Earth's deepest trench is about 7 miles deep. Europa's ocean may be 60 miles deep or more. The water is held beneath ice that may be 10 to 20 miles thick, though in some regions it may be thinner. The ocean stays liquid because Europa is stretched and compressed by Jupiter's gravity. This process is called tidal heating. The moon flexes as it orbits. The movement creates heat inside. That heat prevents the ocean from freezing solid. The same process happens with Enceladus. Enceladus has geysers that shoot water vapor and ice grains into space from cracks near its south pole. We do not need to dig or drill to know there is water. The geysers spray it out. When a spacecraft flew through these plumes, it detected organic molecules and salt. That suggests the water interacts with rock on the ocean floor. On Earth, when water interacts with rock at the ocean floor, hydrothermal vents form. These vents release heat and minerals. They create environments where life thrives, even without sunlight. Some scientists think life on Earth may have begun near vents like these. If similar vents exist on Europa or Enceladus, they could support simple organisms. The conditions would not require sunlight. They would only require water, heat, and the right chemistry. We often talk about life in terms of what is familiar. Plants, animals, and microbes on Earth all depend on sunlight at some level. But sunlight is not required for life in general. Life requires energy. On Earth, energy can come from chemicals deep in the ocean. The same could happen in a hidden ocean under ice. To picture what such a place might be like, imagine descending through miles of ice into darkness. Above is a frozen ceiling. Below is open water. There are no waves because there is no wind. The water is still. except for currents driven by heat from below. If vents exist, they release minerals into the water. Around them, life could cluster the way it does on Earth's seafloor. These may be simple organisms, such as bacteria or single-cell life. They would not build complex structures or send signals into space. They would simply live. If life exists there, it may never know the concept of stars or sky. It may live in a world of darkness and pressure. This kind of life would not resemble us, but it would still count as life. It would mean we are not alone in the universe, even if the neighbor is quiet and distant. Europa's ice moves. It shifts and cracks. Sometimes the ice surface shows signs of rising and falling. That suggests that material from the ocean may reach the surface. If this happens, we could study samples without drilling. We would analyze the chemistry and look for patterns that suggest metabolism. Missions are being planned to fly near Europa and take close measurements. They will not land at first. They will observe from orbit. The goal is to understand the thickness of the ice and the activity below it. Enceladus makes the study easier by releasing its ocean into space. When a spacecraft flew through the plume, it carried instruments able to examine the particles. It found water, salts, and organic compounds. These results do not prove life, but they show that the building blocks for life are present. They also show that the ocean interacts with rock. That interaction is key. It means the environment has energy gradients. Life needs gradients to power chemical reactions. Other moons may also have oceans. Ganymede and Callisto, which orbit Jupiter, may have layers of liquid water trapped between ice layers. Titan, one of Saturn's moons, has a surface of liquid methane and ethane lakes. Beneath that, it may also have a water ocean mixed with ammonia. Each of these environments is different. Some are warmer, some colder, some more chemically rich. The universe does not make one kind of ocean, it makes many. The search for life is not only about finding organisms, it is about understanding environments. When we learn how oceans form on icy moons, we learn how common they may be. If internal oceans are common, then potential habitats for life may be common. That changes how we view the universe. Life might not be tied to the narrow set of conditions we see on Earth's surface. It may adapt to places we once assumed were too harsh. The term habitable does not mean comfortable. It means possible. A sealed ocean beneath ice is possible. It holds water, heat, chemistry, and time. Time is important. Life on Earth began early and developed gradually. If Europa or Enceladus have had oceans for billions of years, that time may have allowed complexity to emerge. We do not know. We need to look. What we do know is that oceans under ice challenge our assumptions. They show that surface conditions do not tell the whole story of a world. A frozen shell does not mean a dead interior. It may be a crust hiding motion, heat, and chemical exchange. It may be a lid over an ocean that has never seen light, but has everything needed to sustain life of its own design. When a massive star reaches the end of its life, it collapses. If the star is large enough, its core compresses under its own gravity. Electrons and protons merge into neutrons. What is left is a neutron star. It is dense in a way that is hard to describe with everyday experience. A teaspoon of neutron star matter would weigh billions of tons. The entire star may be only about 12 miles across, yet contain more mass than the sun. Some neutron stars spin. They spin fast. They can rotate many times per second. As they spin, they emit beams of radiation from their magnetic poles. If one of these beams sweeps past Earth, we see a pulse of light. The pulses repeat at regular intervals. And neutron stars that do this are called pulsars. Their timing is so steady that their pulses can be more precise than atomic clocks. When pulsars were first discovered in 1967, the signals were so regular that the scientists who saw them did not think they were natural at first. The pulses came every 1.3 seconds, steady and unwavering. The research team labeled the first signal LGM-1. LGM stood for Little Green Men. The label was not a claim, just an acknowledgement that the signal looked intentional. Later, when more such signals were found, the explanation became clear. Rotating neutron stars were responsible. The regular pulse comes from the rotation. The beam of radiation is like a lighthouse beam. The neutron star is not sending a message. It is simply rotating with a strong magnetic field. But the effect is striking. It feels like a message because it repeats with precision. It is a steady rhythm in the quiet of space. Some pulsars slow down over time. Others maintain their speed. Some glitch, suddenly changing their rotation rate for reasons linked to stresses in the crust. These changes are small but measurable. By tracking how a pulsar slows, we learn about its internal structure. The crust, the superfluid interior, and the magnetic field all influence how the star behaves. We cannot see inside, but the pulses serve as a record of what is happening. Not all pulsars are steady. Some pulsars switch on and off. They pulse for a while, then go quiet, then pulse again. The mechanism behind this behavior is not fully understood. It may relate to changes in the magnetic field or the movement of charged particles around the star. When the pulses stop, it is as if the lighthouse beam goes dark. When they resume, the clock starts again. There are also pulsars in binary systems. These pulsars orbit another star. When matter from the companion star falls onto the neutron star, the rotation can speed up. These are called millisecond pulsars. They can rotate hundreds of times per second. Their timing is so exact that they are used to test physics on large scales. Groups of pulsars are used to detect gravitational waves by looking for tiny shifts in their timing. A pulsar's beam can travel across the galaxy. It can cross vast distances where there is no matter to block it. When the beam reaches Earth, our telescopes collect it as radio waves. To us, the signal arrives as a repeating pattern. The distance does not change the rhythm. It only changes the strength of the signal. Imagine standing on a coastline at night. You see a lighthouse far out to sea. The light rotates and flashes, steady and clear. You may not know what the lighthouse looks like during the day. You may not know the structure of the island it sits on, but you know there is something out there, turning, repeating. The beam is the only visible sign of the structure that produces it. Pulsars also serve as markers. Because their timing is so steady, they are used as a kind of map. If we measure the arrival time of pulses from multiple pulsars, we can locate our position in space. Some spacecraft navigation plans include pulsars for this purpose. In principle, a spacecraft could use pulsars to determine its location anywhere in the galaxy, the way sailors once used stars on Earth's oceans. There are pulsars that behave unlike the standard model. One example is the magnetar. A magnetar is a neutron star with an extremely strong magnetic field. Its field is so strong that it can alter the arrangement of atoms. Magnetars can produce bursts of X-rays and gamma rays. Their pulses can vary in patterns that are harder to explain. The field may twist, flare, or rearrange itself. When this happens, the star can release energy suddenly. These events remind us that neutron stars are not static. They are physical objects with internal dynamics we are still learning to describe. Fast radio bursts, or FRBs, are another puzzle. They are short bursts of radio waves that last only milliseconds. Many of them appear once and never repeat, but a few repeat in irregular patterns. Some evidence suggests that at least some FRBs may come from magnetars, but the process that creates the bursts is not fully known. The bursts are powerful. They carry more energy in a short moment than the sun releases in days. The brevity adds to the mystery. It is like hearing a knock in the night with no follow-up. The idea of a pulse makes us think of intention, a heartbeat, a signal, a message. But nature can create rhythm without intention. That does not make the rhythm less striking. It shows that the universe contains structure in places where we might expect only chaos. If you were standing on a planet near a pulsar, the sky would flicker with the sweep of radiation. The light would not look like daylight. It would come as bursts, regular and sharp. The pulsar would dominate the sky even if it were small in appearance. Time would feel shaped by the rhythm. Day and night would not matter. The pulse would define intervals. In deep space, where distances are large and silence is common, a repeating signal stands out. Pulsars are not speaking, but they create patterns that travel. These patterns reach us across thousands of light years. We listen not because we expect a message, but because the universe is offering a clock that never sleeps. A star has a life cycle. It forms from gas, shines for millions or billions of years, and eventually runs out of fuel. For many stars, the end comes with a supernova. The star's core collapses, and the outer layers explode outward. The explosion is bright. It can outshine an entire galaxy for a short time. After the explosion, only a remnant remains, such as a neutron star or a black hole. The star should not still be shining in the same way after this point. The event marks the end. But there are cases where a star appears to explode and then continues to exist. It is as if the star refuses to follow the usual sequence. The light curve, the pattern of brightness before, during, and after the explosion, does not match what our models expect. The expected collapse does not seem complete. This challenges our understanding of how stars end. One example involves a group of stars called failed supernovae. These are stars that show signs of collapse but do not produce a bright explosion. Instead, they seem to dim and fade. The core collapses into a black hole, but the outer layers fall in quietly. Yet, even in these cases, the star should not remain visible afterward. The light should disappear. But in 2009, astronomers observed a star known as N6946 BH1 in the galaxy NGC 6946. It was a large star, about 25 times the mass of the Sun. It brightened slightly, as if preparing to explode, then dimmed and did not return to its original brightness. It should have become invisible, replaced by a black hole. Yet, faint traces of light remained. Something continued to emit energy. That emission did not fit the expected model of a silent collapse. Another case involves stars that explode more than once. These are called pulsational pair instability supernovae. In these stars, the core reaches temperatures so high that gamma rays convert into particle pairs. This reduces pressure and causes the core to contract. The contraction heats the core more, and part of the star explodes, but not all of it. The star loses material but survives. Then it stabilizes until the cycle repeats. The star may explode several times before finally ending. Each explosion looks like a supernova, even though the star still exists in between. A well-known example is the star known as Eta Carinae. In the 1800s, it flared dramatically. It became one of the brightest objects in the sky, but it did not die. It remains a massive, unstable star, still visible today. It released huge amounts of gas, in which formed the homunculus nebula around it. The star did not follow the expected path. It survived a catastrophic event. Then there are the supernova imposters. These events look like supernovae in brightness, but do not destroy the star. Instead, they are eruptions. The star throws off a large amount of mass, but remains intact. These eruptions can resemble the early stages of a supernova because the expelled gas glows brightly. Afterward, the star continues to shine, though often changed. To understand why these stars behave this way, it helps to think about stellar balance. A star maintains itself by balancing inward gravity and outward pressure from nuclear fusion. When fusion slows or stops, gravity wins. The star contracts. If the contraction is violent enough, the outer layers explode. But if conditions change gradually or in stages, the collapse may not be final. The star may lose material in bursts and temporarily regain balance. Imagine a structure under stress. It does not collapse all at once. A beam cracks. Part of the structure shifts. Some pieces fall away. The structure holds, but in a weaker form. A star can behave the same way. It can lose mass in repeated events, adjusting each time. These events release energy that travels across space. We see that energy as light. Light curves provide clues because the shape of the curve reflects the physics of the star. A classic supernova brightens quickly, then fades in a predictable way. But some stars show light curves that drop sharply, then rise again, or fade slowly in ways that do not match known processes. These curves suggest ongoing activity after what should have been the final collapse. There is another phenomenon to consider: fallback accretion. When a star explodes, some of the outer material travels outward, but some of it can fall back toward the core. If the core has become a black hole, the falling material can create a disk. The disk emits energy as it spirals inward. The star is gone. The system is not silent. The light may look like the star is still there, but it is a different kind of source. Another possibility is that the star was not a single star. Many stars exist in binary systems. If one star explodes, the companion star can still shine. If we are observing from far away, distinguishing the surviving star from the destroyed one can be challenging. The light may appear as though the exploded star is still shining. Only detailed measurements reveal that the surviving star is the source. These examples show that the end of a star is not always final in a simple sense. The process can be gradual. It can involve multiple changes. The light we see may come from different stages or different parts of the system. The expected brightness patterns are guides, not rigid rules. To picture this, think of a campfire. At first, flames rise and fall. As the fire burns down, the flames disappear. A log still glow. The heat lingers. The fire is not gone, even though the flames are. A supernova is like the flame. The star's collapse is like the coal bed. The visible event is brief. The aftermath can continue to emit energy long after the explosion ends. Stars that refuse to die show us that endings in the universe can be drawn out. The light does not always match the final state. The collapse may not be clean. Some stars fade and return. Some explode more than once. Some leave traces that continue to shine. The timeline of a star's life is not always a straight line. It can bend, stall, flare, or extend in ways that challenge our simple expectations. A black hole forms when a large amount of mass collapses into a very small space. Its gravity becomes so strong that nothing can escape once it crosses a certain boundary. That boundary is the event horizon. Anything that crosses the event horizon cannot return, not even light. This is the core idea of a black hole. It is a region where gravity prevents escape. The phrase black hole comes from this idea. No light comes out. It should be perfectly dark. Yet, we now know that black holes are not completely silent. They are not entirely sealed. They can lose energy over time. This energy escapes in the form of radiation known as Hawking radiation. The concept came from Stephen Hawking in the 1970s. Before his work, most scientists assumed black holes could only grow. They could gain mass by absorbing matter and energy, but they could not lose anything. Hawking showed that the situation is more complex. The key to understanding this starts outside the event horizon. Space is not empty. Even what we call a vacuum contains fluctuations. According to quantum mechanics, pairs of particles and antiparticles constantly appear and disappear. They form, separate for a moment, then annihilate each other. This happens everywhere, including near the event horizon of a black hole. Near the event horizon, something interesting can occur. If a particle and its partner form right on the boundary, one particle can fall into the black hole while the other escapes. When this happens, the escaping particle becomes real instead of disappearing. It travels away from the black hole as radiation. From our perspective, it looks like the black hole has emitted something. This does not violate the rule that nothing escapes from inside the event horizon. The escaping particle was never inside. The process happens at the edge, but the effect is that the black hole loses a small amount of mass. Over long periods of time, a black hole can shrink because of this radiation. The smaller the black hole gets, the stronger this effect becomes. Large black holes lose energy very slowly. Tiny black holes would evaporate faster. This radiation is extremely weak for black holes the size of stars. It is too faint to detect with current instruments, but the math is clear. The black hole is not a completely closed system. It interacts with the universe through the structure of space itself. The idea that a black hole can leak energy raises a deeper question. What happens to information that falls into a black hole? Information in physics refers to the details that describe the state of matter. For example, the arrangement of atoms, the quantum states of particles, the way energy is distributed. When something falls into a black hole, we cannot see it anymore. But physical laws suggest that information cannot be destroyed. It can change form, but it cannot vanish. This is known as the conservation of information. So what happens to the information inside a black hole if the black hole slowly evaporates? This is called the information paradox. If the black hole eventually disappears, and if all the matter inside is lost, then the information appears lost, would break the laws of physics. But if the information somehow escapes in Hawking radiation, then the radiation must carry structure. However, the early models of Hawking radiation suggest it is random without structure. That means the radiation alone cannot carry the information back out. This conflict between quantum mechanics and general relativity is one of the biggest problems in modern physics. It forces us to consider that our understanding of either gravity, quantum mechanics, or both is incomplete. There are several possible ways to resolve this paradox. One idea is that the information is encoded in the Hawking radiation in a way we do not yet understand. Another idea is that the information remains stored at the event horizon itself. This leads to the concept known as the holographic principle. It suggests that everything inside a black hole may be described by information stored on the surface, not the volume. In this view, the black hole is not a simple container. It is more like a library whose books are written into the boundary. To picture this, imagine writing a story on the outside of a sphere. The inside is full of space, but the content that describes it is stored at the surface. The holographic principle suggests that the universe itself may operate this way. Space may contain volume, but the information that defines it may be stored on two-dimensional surfaces. This is a hard idea to relate to everyday experience because our senses are built around 3 dimensions. But mathematics shows that this is possible. Another idea involves quantum entanglement. When 2 particles are entangled, what happens to one affects the other instantly, no matter how far apart they are. If particle pairs near the event horizon are entangled, some of the information from the matter inside could be transferred outward through their connection. The mechanism is not yet understood, but entanglement is real. We observe it in laboratories. It suggests that space may have connections we cannot see. Some researchers have proposed that what we think of as the interior of a black hole may not exist in the way classical physics describes it. The concept of a singularity may be replaced by something new, where space and time rearrange in forms we cannot yet describe. If this is true, the idea of a black hole leaking may not mean that matter escapes. It may mean our definitions of inside and outside need revision. A black hole is a place where 2 frameworks of physics meet: gravity, which describes space and time, and quantum mechanics, which describes particles and forces. They do not yet form a single system. The black hole sits where the mismatch is exposed. It is a silent reminder that the universe follows rules we are still learning to articulate. Hawking radiation does not appear explosive or energetic. It is patient. It works over long spans of time. For a supermassive black hole, the evaporation time exceeds the current age of the universe many times over. But the process is happening. The leak is slow, steady, and built into the structure of space. The black hole looks still from a distance. It makes no sound. It emits no visible light. Yet space around it flickers with the quiet hint of particles forming, separating, and sometimes escaping. The leak is not loud, it is subtle. It is a whisper of the underlying rules at work. There are planets where conditions differ so much from Earth that familiar materials take on unfamiliar roles. On some worlds, carbon does not form soil, wood, or smoke. It forms solid diamonds. On certain giant planets, the pressure inside is so high that carbon compresses into crystal. The result is diamond rain. These diamonds fall through deep layers of gas and liquid. They sink toward dense cores where heat and pressure continue shaping them. To understand how this happens, consider carbon on Earth. At normal pressures and temperatures, carbon forms graphite, coal, or organic molecules. When we want to make diamond, we apply high pressure and high heat. Deep in Earth's mantle, where diamonds form naturally, the pressure is millions of times higher than atmospheric pressure at the surface. The heat is extreme. Under these conditions, carbon atoms lock into a rigid, repeating structure that creates diamond. Now consider the interior of a gas giant like Neptune or Uranus. These planets are made mostly of hydrogen, helium, carbon, nitrogen, and oxygen. The upper layers are cold, but as you move deeper, pressure and temperature increase. At a certain depth, the pressure can reach levels even higher than those in Earth's mantle. Carbon in these conditions does not stay in the forms we know here. It reorganizes into diamond. Research suggests that lightning in the atmospheres of Uranus and Neptune may split methane molecules into carbon and hydrogen. The carbon can clump into soot-like particles. As these particles fall deeper, they encounter higher pressure. The suit transforms into graphite. Deeper still, graphite becomes diamond. These diamonds grow as they fall. They become pieces large enough to qualify as gemstones by any standard. But no one will ever mine them. There is no solid surface to reach and no stable place for humans to stand. The diamonds fall into an environment no person could survive. Imagine the descent. Near the top of the atmosphere, the environment is cold and dim. Winds move in wide patterns. Methane gives the clouds a blue tint. Carbon forms into small particles, too small to see with the eye. They drift downward. The deeper they fall, the higher the temperature and pressure. At some depth, the drift becomes a freefall. The particles are no longer drifting. They are falling through layers that feel like fluid, even though the composition is still gas-like. At this deeper level, the carbon transitions into diamond. The pressure holds the atoms tightly together. The fall continues. The diamonds sink like hailstones in a storm. Their shapes are likely irregular. Some break, others may merge. Many continue falling until they reach a region where the temperature becomes high enough to melt them. Liquid carbon may pool around the core. There could be oceans of liquid carbon beneath the diamond rain. Experiments here on Earth help support this idea. Scientists have used high-pressure chambers and lasers to compress methane to pressures like those inside Neptune. When they do, diamond forms. These lab conditions last only fractions of a second, yet the result is clear. Under the right pressure, carbon prefers the diamond structure. These findings suggest that diamond rain is likely common inside giant planets. Neptune and Uranus are the closest examples, but there are many exoplanets orbiting other stars that have similar compositions. Some exoplanets may have even higher pressures. They could have layers where diamonds form more easily in larger quantities. Some might have solid diamond crusts. Others might have entire interiors made mostly of diamond. The idea sounds unusual at first, but it follows the same logic that makes graphite become diamond under pressure on Earth. The difference is scale. On these worlds, diamonds are not rare. They are a natural result of physical conditions. The value we give diamonds on Earth does not apply there. Scarcity defines value here. Demand gives it meaning. On a planet where diamonds fall from the atmosphere like heavy rain, the material does not carry symbolic importance. It is simply part of the planet's chemistry. There is another layer to consider. The diamond rain may influence how these planets behave. As diamonds sink, they carry heat downward. Movement of material inside a planet affects circulation, magnetic fields, and temperature distribution. The presence of diamonds may help explain why Uranus and Neptune give off less internal heat than Jupiter or Saturn. The falling crystal layers might transport heat in ways we do not fully understand. If we imagine a probe descending into Uranus or Neptune, the journey would be harsh. The probe would pass from cold, windy layers into regions of crushing pressure. Eventually, the structure would fail. But before that happens, sensors might detect the change in material structure. Light scattering, density shifts, or shock patterns could signal crystal formation. But no probe has yet made the attempt. The evidence we have comes from experiments, models, and mathematics. The idea of diamond rain invites us to rethink what is common and what is rare in the universe. On Earth, diamonds are formed over long times under special conditions. We dig for them, process them, and assign them value. On some planets, the universe produces diamond automatically. It forms from simple carbon under the weight of layers of gas and gravity. It does not need time in the same way. It just needs pressure. If a person could hold one of these extraterrestrial diamonds, the diamond would look familiar. The structure would be the same. The atoms would be arranged in the same pattern. The difference is in how it came to exist. It would not have formed in rock. It would have condensed in mid-fall, shaped by gravity rather than by stone. The existence of diamond rain does not make these planets more welcoming or more accessible. It does not suggest wealth hidden in the outer solar system. It simply shows that the universe builds materials in many ways. It shows that common processes, scaled up, can produce results that feel extraordinary at human scale. The universe does not treat diamond as treasure. It treats diamond as a form carbon can take under pressure. When we look at the night sky, we see patterns. Some patterns are familiar because we learned them as constellations. The Big Dipper, Orion, Cassiopeia. These groups of stars are not physically connected in space. They only appear grouped from our point of view on Earth. Constellations are shapes we draw across distance. They are ideas projected on real stars. But constellations are not fixed. Stars move. Their positions shift slowly over thousands of years. The shapes we use today were not always the same. If we could watch the sky change in slow motion, constellations would drift and stretch. An archer would bend into a new pose. A hunter would lose a shoulder or gain another line of stars. The sky holds motion that takes longer than a lifetime to notice. There are groups of stars that look like patterns forming, but not yet recognized. Some of these patterns may become constellations in the distant future, long after we are gone. Some may have been constellations to civilizations older than the written record. Names now forgotten. When we talk about unfinished constellations, we talk about shapes that appear incomplete, waiting for stars still moving into place. A star cluster can begin to form a recognizable pattern if its stars share a similar location and movement. Many clusters are born from the same cloud of gas. They move together as gravity slowly spreads them apart. Pleiades is one example. Today it looks like a small group of bright stars near Taurus. But thousands of years ago, people in different cultures saw different shapes in it. Some saw seven sisters. Some saw a group of birds. Some saw seeds scattered in the wind. The pattern changed with interpretation. Now imagine a set of stars slowly drifting into a clearer outline. At the moment, we might not recognize the shape. It may look ordinary, just part of the background. But given enough time, the stars may line up in a way that suggests a simple figure, an animal, a tool, a person. If a future culture looks up, they may give it a name. They might tell stories about it. They might draw myths around it. The sky becomes part of their language. One example of a possible unfinished constellation can be seen in the group of stars near the constellation Cygnus. Several stars are moving in a way that may create a longer, more defined line in the future. Right now, the pattern is faint. It does not stand out. But because the stars share a direction of motion, the line will stretch. It may become something more recognizable in tens of thousands of years. Our eyes are not trained to see what the sky is becoming. We see what it is now. There are also constellations that once existed and have faded. Ancient people saw patterns that no longer look the same today. Their stories described shapes that modern observers cannot match. The stars moved. The patterns changed. What was once a clear image became scattered. The sky erased the drawing slowly, without intent. If we consider how humans use constellations, we see that patterns help us navigate. Early sailors used them to travel across oceans. Farmers used them to track seasons. Constellations served as reminders and markers. But the shapes reflect culture as much as astronomy. A hunter-shaped constellation means something different to a society that does not hunt large animals. A pattern shaped like a plow means something only to people who use plows. If another society looked at the same stars, they might see something different. Now imagine a civilization far older than any we know. They might have watched the sky long before writing existed. They could have named patterns that vanished before our constellations were named. Their sky stories may have spoken of patterns we cannot reconstruct. The unfinished constellation may have been finished for them. The shape we see as incomplete may have been clear before the stars drifted. Time has erased their version of the sky. We only see what remains. We can think about this using a simple comparison. Imagine a painting that has been weathered. Some details are sharp, others are faded. We see the outline, but not the full picture. The sky is like that. We see the stars as they are now, not as they were or will be. We are in the middle of a story written across millions of years. The motion of stars is slow, but not random. Each star follows its own path through the galaxy. Some move toward us, some move away. Some rise in brightness as they evolve, others dim. Over time, these changes shift the patterns we see. The unfinished constellation is a pattern mid-formation. It will not finish in human time. It will continue to shift after we are gone. If we could watch the night sky as a time lapse over millions of years, constellations would flow like ink on water. Shapes would form and dissolve. The sky would never hold still. The constellations we draw now are temporary. They exist because we live during this brief span of time. There is another way to consider this. When we look at the stars forming a shape, we assume they belong together, but the light we see left each star at different times. Some of the light we see tonight began traveling before the first cities were built. Some began long before humans existed. The pattern we see is not only spatial, it is temporal. We are seeing stars at different ages, frozen into a simultaneous view because of distance. If one of those stars reaches the end of its life and goes supernova, the shape will change. The constellation will lose a point. It may no longer resemble the figure we assign to it. The unfinished constellation can lose stars as easily as it gains them. The patterns are temporary arrangements of light. A person standing on a distant planet, orbiting a star on the other side of the galaxy, would see a different sky. They would draw different patterns. They might find meaning in groups of stars we never consider connected. Their constellations might seem unfinished to them too, changing as their stars move. The sky is always in motion, and patterns are always forming. The unfinished constellation is not waiting for us to name it. It is simply continuing its slow transformation, guided by gravity and time. The shape may never be fixed. It may always remain in progress. When we imagine a galaxy, we picture stars, spirals of bright light, dense bands of glowing dust, points of color set against black space. The idea of a galaxy without stars seems contradictory. A galaxy should be defined by the stars inside it. Yet observations suggest that galaxies can exist with almost no visible stars. These are sometimes called dark galaxies. They contain gas, dust, and large amounts of dark matter, but little or no starlight. They move and interact with other galaxies, They shape structure in the universe, but they do so quietly, without the glow that usually marks a galaxy's presence. To understand a dark galaxy, it helps to think about what holds a galaxy together. Gravity is the main force. Most of the gravity in a galaxy does not come from stars. It comes from dark matter. Dark matter does not emit or reflect light. We know it exists because of how it influences motion. If we measure how fast stars orbit the center of a galaxy, the speeds are too high for visible matter alone to account for them. Something unseen is contributing gravity. That unseen mass is dark matter. If a galaxy forms in a region where there is enough dark matter, but not enough conditions to trigger star formation, the galaxy can exist without shining. Gas can fill the galaxy. Dust can move in long rivers. The structure remains, but the stars do not ignite. Star formation requires gas to cool and collapse. Cooling depends on radiation and interactions among particles. If conditions prevent that cooling, gas can remain spread out instead of condensing into dense regions. Without dense regions, no stars form. Researchers have observed candidates for dark galaxies through indirect means. One approach involves looking at how these galaxies affect visible galaxies nearby. When two galaxies interact, their gravity pulls on each other. This pull can stretch visible matter into long streams called tidal tails. If we see a tidal tail with no bright companion galaxy, it suggests something invisible is interacting. That invisible presence may be a dark galaxy. Another clue comes from hydrogen gas. Even if a galaxy has no stars, it can contain neutral hydrogen. This hydrogen emits a specific radio signal at a wavelength of about 21 centimeters. Radio telescopes can detect that signal. If we detect hydrogen gas arranged like a galaxy, but no visible stars, the object may be a dark galaxy. One example is the object known as Virgo HI 21. It was found in the Virgo cluster and shows strong hydrogen emission, but no starlight. It appears to be moving and rotating like a galaxy. Something must be holding the gas together. The most likely answer is dark matter. The object may be a galaxy with gravity, but no stars. To picture a dark galaxy, imagine a cloud the size of the Milky Way, but invisible. It has structure. Gas swirls in giant cycles, like weather systems on a planet, but on a scale of thousands of light years. Gravity shapes the gas into arcs and filaments. Dust gathers in certain regions, but nothing ignites. There is no glow, no star clusters, only motion. If a person could travel into such a galaxy, they would see almost nothing. The sky would remain dark. The environment would be cold. The gas would be thin, far thinner than any atmosphere. The galaxy would not announce itself. Its presence would be felt only through how it influences motion. A spaceship's course would bend because of gravity. A probe would detect hydrogen through radio signals, but there would be no visible light. Dark galaxies offer clues about how galaxies evolve. In the early universe, many galaxies were small and gas-rich. Others may have remained dark. If we want to understand how galaxies grow into the forms we see today, we need to understand what happens in the dark stages. Dark galaxies might be building blocks that never completed the process of star formation. They might be fossils of an early era. Imagine a young galaxy forming in a region where gas is heated by ultraviolet radiation from nearby stars or black holes. The heat prevents the gas from cooling. A gas cannot collapse into star-forming clouds. The galaxy remains dark. Over time, if conditions change and the gas cools, stars could form later. A dark galaxy could become a bright one, or it may never cross that threshold. There are cases where a dark galaxy interacts with a visible galaxy. When this happens, gas can be stripped from the dark galaxy and pulled into the visible one. The visible galaxy gains new material to form stars. The dark galaxy weakens. In this way, dark galaxies may contribute to star formation in other galaxies, even if they do not form stars themselves. One way to think about this is to picture a slow wave, not of water, but of mass. A dark galaxy passes near another galaxy. The gravity between them forms a bridge of gas. The bright galaxy pulls the gas in. New stars form in the bright galaxy. The dark galaxy becomes fainter still. The interaction shapes both objects, even though one remains unseen. We also look at dark galaxies to test models of dark matter. If dark galaxies exist in large numbers, it would support certain versions of cosmological theory. If they are rare, it would support others. Their presence helps map the unseen framework that holds the universe together. Much of the structure of the cosmos may be built from dark matter, with visible galaxies acting like beads strung along deeper, invisible threads. The idea of a galaxy without stars is not a fantasy or metaphor. It is a physical possibility supported by evidence. We cannot see such galaxies directly with our eyes or ordinary telescopes, but we see their motion. We see their effect on surrounding systems. The universe does not require light to build structure. Gravity alone can shape a galaxy. The stars are an added layer, not the foundation. A galaxy without stars is not empty. It is a slow, quiet motion of gas, dust, and dark matter. It is a presence defined not by what it shines, but by how it bends the space around it. A comet follows a path shaped by gravity. When it moves through a solar system, the sun's gravity bends its motion into an orbit. Some comets return after a few years. Others take centuries. Some return only once because their orbit carries them so far that they never come back. The timing is not random. It can be calculated. If we know a comet's speed and distance from the sun, we can predict when it will return. The orbit should remain steady unless something changes it, but there are comets that come back sooner than the calculations say they should. These comets do not follow their predicted timetable. They return ahead of schedule. The difference is not minutes or days. Sometimes the difference is years. When this happens, astronomers must look for something that changed the comet's orbit. The question is what force acted on the comet that we did not include in the original math. One of the first cases like this was noticed when astronomers tracked Comet 3D Biela. Its orbit suggested it should return every 6.5 years. For a time, it did. Then it began returning slightly sooner. The shift was small at first. Later, the change grew. Eventually, the comet broke apart. Pieces took different paths. Some produced showers of meteors on Earth. But the earlier changes in timing came before it broke. Something influenced its path before the visible breakup. A comet is not a solid rock. It is a mix of ice, dust, and frozen gases. When it gets close to the sun, the ice turns to gas. The gas escapes into space and forms the comet's tail. But when the gas escapes, it produces a small push. The push is not strong, but over time, it changes the comet's motion. If the gas escapes more on one side of the comet than the other, it acts like a jet. The comet accelerates slightly. The orbit shortens. This is known as a non-gravitational force. It is not caused by the sun pulling, but by the comet pushing itself. Many comets show this behavior. but the effect is usually small. The unexpected returns stand out because the effect seems too strong to come only from outgassing. The timing changes more than expected. Something else may be acting. Another possibility involves the shape of the comet. If the comet rotates, and parts of its surface heat unevenly, the gas release may vary across its orbit. The rotation can shift the direction of the expelled gas over time. This makes the jet effect irregular. It does not produce a steady push, but a pattern that changes. The changing pattern makes calculations difficult. There are also comets that return too soon, without strong visible outgassing. These comets do not produce long tails. They look faint and inactive. If they are not releasing much gas, the jet effect should be weak. Yet the orbit still shifts. This suggests internal changes. A comet may hold volatile materials deep inside. A crack may open and allow gas to escape suddenly. The comet gains a push even if the surface appears calm. We also consider gravitational influences from other bodies. A comet may pass near a planet. The planet's gravity bends the comet's path. If the comet passes Jupiter, the effect can be large. Jupiter's gravity is strong. A small change in the comet's trajectory can shorten the orbit. But when a comet returns too soon, and no planetary encounter has been recorded, the cause remains unclear. To study this, scientists track the comet's position over time. They look for patterns. They examine how the comet brightens and dims as it approaches and leaves the sun. Brightening can indicate increased gas release. Dimness may indicate a quieter phase. If the brightness changes do not match the timing shift, the explanation must lie elsewhere. Some comets appear to lose mass in bursts. A sudden release of material can push the comet. The timing of that push matters. If it happens when the comet is near the sun, the effect is stronger. The orbit changes more. If it happens far from the sun, the effect is weaker. Comets are complex objects with fragile structures. A crack or collapse inside the nucleus can change the distribution of mass. A shift in mass changes rotation. Rotation changes how gas escapes. The motion changes in steps rather than smoothly. Imagine a wheel with uneven weight. When it rolls, the weight shifts and the wheel wobbles. The path becomes unpredictable. A comet behaves in a similar way. The interior is not uniform. The comet changes as it travels. Pieces break off, cavities open, surfaces evaporate. The orbit is the result of both gravity and these internal changes. We also consider that some comets may come from groups. A single comet may once have been part of a larger body. If pieces separate, each piece follows a slightly different path. When one piece returns early, it may appear to violate the expected orbit. The orbit is not wrong. The object has changed. We are seeing something new where we expected something familiar. There have been rare cases where a comet's early return suggests an unknown object influenced it. A small asteroid or fragment not yet observed may have passed nearby. Gravity acted briefly, but changed the path enough to alter the timing. Because the object was small and dark, no one detected it. The comet's orbit became the record of the encounter. When a comet returns too soon, the first assumption is that outgassing changed the orbit. Often, this is correct, but sometimes the magnitude of the shift challenges the explanation. It requires examining the comet closely over multiple returns. Some comets are watched for decades or centuries. The record becomes part of our understanding of how ice behaves in deep space. A comet that disobeys its predicted orbit is not breaking physical laws. It is showing that the simple model does not capture the full behavior of the object. The comet is changing. The orbit is responding to forces that are subtle, irregular, and layered. The early return is a sign of motion influenced by internal structure, rotation, gas release, and encounters we may not have seen. We expect orbits to follow clean curves. The universe is more dynamic. A comet is not a cold, fixed object. It is active, even when it looks still. Its path carries the record of its changes. The timing tells us that something happened, even if the event left no visible mark. When radio telescopes first began scanning the sky, scientists expected to find silence. They expected the spaces between stars and galaxies to return nothing. But when they listened at certain frequencies, they heard a faint background signal. It did not come from one direction. It came from all directions. No matter where the telescope pointed, the signal was there. It did not strengthen or weaken based on location. It behaved like a constant presence. Today, this signal is known as the cosmic microwave background. It is radiation left over from the early universe. But before it was understood, it appeared to be a broadcast with no sender. The discovery happened in 1965, when two radio engineers, Arno Penzias and Robert Wilson, were testing an antenna designed for communication. They kept detecting a faint noise. They cleaned the antenna. They adjusted their equipment. The noise did not go away. They checked for interference from nearby cities. They checked for transmission from the ground. Nothing changed the signal. It was always present. The signal had the same strength in every direction. It did not point to a star, planet, or galaxy. It behaved as if the universe itself was broadcasting it. When scientists examined it more closely, they realized the signal fit a theoretical prediction made years earlier. The prediction said that if the universe began in a hot, dense state and expanded, the leftover heat would remain faintly in space. The expansion would stretch the radiation into microwave wavelengths. That leftover heat is what the antenna detected. The signal is uniform, but not perfectly uniform. There are tiny variations in temperature. These variations are important. They show that the early universe was not smooth. Some regions were slightly denser. Over time, gravity amplified these differences. Dense regions became galaxies and clusters. Less dense regions became the empty spaces between. The signal carries the pattern of these early differences. It is like a faint map of the universe when it was only a few 100,000 years old. If we imagine listening to the signal with our ears, it would sound like static. The static on an analog television contains some contribution from this background. When a television is tuned to no channel, some of the noise is this radiation. People once saw and heard it without knowing what it was. The signal comes from the moment when the universe first became transparent to light. Before that moment, matter was too dense. Light scattered constantly. As the universe expanded and cooled, atoms formed. Light could travel freely. That light has been traveling ever since. The universe expanded and stretched the light into lower energy wavelengths. We detect it as microwaves. What makes the signal unusual is that it is not from one object. Most signals in astronomy come from a source. A star emits a spectrum. A galaxy emits light that shifts depending on motion. A pulsar emits radio pulses. A quasar emits strong radiation from matter falling into a black hole. Each signal points to a physical location. The cosmic microwave background does not. It comes equally from all directions. It fills the universe. This does not mean the signal has no origin. It has an origin, but the origin is not a point in space. The origin is a moment in time. That moment is when the universe cooled enough for photons to escape. Because the universe has no center in the traditional sense, the radiation appears to come from everywhere. We are inside the radiation, not observing it from the outside. To picture this, imagine being inside a room lit by glowing walls. The light reaches you from all sides. If you do not know the walls exist, you might think the light comes from everywhere. The room is the universe. The walls are the moment of cooling. The light is the signal. The small variations in the signal are measured with great precision. Satellites like Comet, WMAP, and Planck mapped these variations. The maps show regions slightly warmer and cooler. The differences are tiny, but they show the structure of the early universe. They tell us how fast the universe expanded. They tell us how much matter and energy it contains. They tell us that most of the universe is made of matter we cannot see. The signal does not explain dark matter directly, but the pattern it forms tells us dark matter existed early on. The signal also raises questions. One question involves the uniformity itself. The universe appears too uniform. Regions that are now far apart should not have been able to influence each other, given the speed of light. Yet they share nearly the same temperature. This problem led to the theory of cosmic inflation. Inflation suggests that the universe expanded faster than light in the first fraction of a second. This rapid expansion smoothed out differences. Then the expansion slowed. The uniformity we see is a result of this early stretching. Another question is whether the signal contains any imprint from events before that early moment. If something existed before the expansion phase we call the Big Bang, traces might appear in the background. Some researchers search for unusual patterns, such as circular rings or temperature alignments. These patterns could suggest earlier cycles of the universe. So far, no clear evidence has confirmed this. The search continues. The signal that comes from everywhere is not a message in the sense of communication. It does not carry intention. It is a record. It holds information about conditions the universe once had. It speaks without meaning to speak. It persists because space preserves what travels through it. If we turned off every star, galaxy, and planet, the background radiation would remain. It is the quiet floor beneath all other signals. It is an echo of a time when the universe was bright and dense. Now it is faint and cool, but it does not disappear. It fills the sky like a memory that the universe cannot forget. Most of the universe is cold. Space does not have air or solid surfaces to hold heat. Objects in space gain or lose temperature by absorbing or releasing radiation. Without a source of heat, anything exposed to open space cools. Even so, the universe has a temperature standard. That temperature comes from the cosmic microwave background, the leftover radiation from the early universe. It sets a baseline of about 2.7 Kelvin. Nothing in open space should be colder than that without active cooling, because that radiation fills all space. Yet there is a region called the Boomerang Nebula that tests this idea. In this nebula, gas reaches temperatures lower than the cosmic background. It reaches about 1 Kelvin. That is just 1 degree above absolute zero, the theoretical limit where motion stops. To understand why this region is so cold, it helps to know what the Boomerang Nebula is. It is a cloud of gas in the Milky Way. At its center is a dying star. The star has entered a stage where it sheds its outer layers. This happens when the star runs out of fuel and cannot support the weight of its own atmosphere. The outer layers expand and drift into space. As they expand, they cool. Expansion lowers temperature in the same way that compressed gas grows hot and stretched gas grows cold. We see a similar effect with spray from a compressed can. When the spray leaves the nozzle, it cools fast because the gas expands. In the nebula, a similar process happens, but on a much larger scale and for a longer time. The gas flows outward at high speed. The rate of expansion is fast enough that the gas cools below the temperature of the cosmic background. The radiation from the early universe cannot warm the gas fast enough to keep its temperature up. The nebula becomes colder than the universe that surrounds it. The star at the center drives the process. It is losing mass rapidly. The outflow of gas forms a thin envelope stretching out around it. The gas expands into near-empty space. When matter spreads out, particles collide less often. With fewer collisions, there is less heat. The temperature drops. In most nebulae, the expansion slows before temperatures reach such extremes. But in the Boomerang Nebula, the outflow remains fast. The gas continues to expand without warming from nearby stars. The region becomes the coldest natural environment known. If someone tried to stand inside this nebula, they would not see much. The gas is thin. It does not block light the way a dense cloud would. It has shape, but the shape is faint. The name Boomerang came from early telescope images that showed a slight curve. Later images revealed a more symmetric hourglass shape. The shape forms because the gas does not expand evenly in all directions. The star may have a companion or a magnetic field that channels the flow. The outflow forms two opposite lobes. Between them lies the star, faint behind dust. The low temperature in the nebula makes it difficult to study. Most instruments detect light or radiation, but cold gas emits little radiation. It absorbs little as well. The lack of emission makes the nebula appear dim. Observers detect it by looking at how the cold gas absorbs or scatters background radiation. The cosmic microwave background passes through it. The gas alters that signal slightly. These changes allow astronomers to measure its temperature. The temperature near 1 Kelvin is surprising because it means the nebula is actively cooler than the environment around it. It is like finding a lake colder than the air and colder than the wind, colder even than the ground beneath it. Something must continually drive the temperature down. The expansion of the gas is that driver. As long as the gas flows outward fast enough, it continues to cool. Once the outflow slows, the temperature will rise. The cosmic background will have time to warm the gas. The region will lose its extreme cold. The star at the center will eventually become a white dwarf. When the gas disperses, the nebula will fade. The coldest known place will not stay the coldest. It is a temporary state created by this stage of stellar evolution. The low temperature exists only while the gas is expanding quickly. This means that similar nebulae may exist elsewhere. The Boomerang Nebula is notable because it happens to be close enough for us to study. Other stars may be shedding gas in similar ways in distant parts of the galaxy. The coldness of this nebula is not a mystery because we do not know what causes it. It is unusual because the conditions that allow it are rare. The balance between expansion, cooling, and background radiation must be very precise. The star must lose mass at a particular rate. The gas must expand without heating by starlight or shock waves. The region around the star must remain quiet. If a nearby star emitted strong radiation, the nebula would warm. If collisions between gas particles increased, the temperature would rise. This cold region reminds us that temperature in space depends on process, not location. The nebula is not far from the Sun in cosmic terms. It is within our galaxy, but distance does not determine temperature. Motion and density do. A region that expands fast loses heat. A region that compresses gains heat. The universe is full of such shifts. Stars ignite when clouds compress. Planets cool slowly when heat moves to the surface. Nebulae glow when radiation excites gas. The Boomerang Nebula cools because expansion outpaces heating. If we consider how fragile this balance is, we see that the coldest place known is a moment in time, not a permanent feature. The star's mass loss will slow. The gas will thin further. The cosmic background will warm the gas slightly. The nebula will rise in temperature. But while the process lasts, the gas remains colder than any natural environment we know of. It is colder than the surface of Pluto, colder than the dark side of the moon, colder than the deepest vacuum chambers we build on Earth, unless they use artificial cooling systems. It is a patch of space where heat has almost no presence, held in that state by motion alone. ... Most objects in space carry magnetic fields. Earth has one, the Sun has one. Galaxies have fields that run through them like invisible threads. But some objects produce magnetic fields on a scale that challenges the limits of matter. These objects are magnetars, a type of neutron star. A magnetar has a magnetic field more than 1 trillion times stronger than Earth's field. At that strength, the field does not just influence charged particles. It changes the structure of atoms. It affects how space behaves. It can twist matter and radiation in ways that do not occur anywhere else. A magnetar begins as a massive star. When the star runs out of fuel, gravity causes it to collapse. The outer layers explode as a supernova. The core collapses into a neutron star, an object so dense that a teaspoon of its material would outweigh mountains. In some cases, the collapsing core retains a rapid spin and builds an extreme magnetic field. The field concentrates because matter is compressed into a small volume. It is the same principle as concentrating magnetic energy in a coil, but on a far larger scale and under far greater pressure. A magnetar is about 20 kilometers wide. That is small compared to Earth, yet its magnetic field can extend many thousands of kilometers outward. The field lines curve across space like invisible scaffolding. Anything that enters the region is affected. Electrons spiral along these lines. Radiation bends. Even the vacuum around the magnetar behaves differently. Under such strong fields, virtual particles in empty space can become real for brief moments. This is called vacuum birefringence. It means the vacuum itself acts like a material that can split or polarize light. To understand the strength of a magnetar's field, consider the energy stored in it. If Earth's magnetic field shifted, compasses would change direction. If a magnetar's field acted on Earth at the same distance as the Moon, it would strip the iron from our planet's core. At much closer distances, chemical bonds would not hold. Atoms would stretch into thin, cylinder-like shapes aligned with the field. Ordinary matter would not behave the same way. Magnetars reveal their presence through bursts of high-energy radiation. Sometimes, the magnetic field becomes unstable. The surface of the magnetar can crack. When that happens, the release of magnetic energy produces a flare. These flares are short but intense. One such flare, detected in 2004 from a magnetar in the constellation Sagittarius, briefly overloaded instruments on satellites. The flare came from tens of thousands of light-years away. Yet detectors on Earth saw it clearly. The crust of a magnetar is under constant stress from the magnetic field. The field tries to twist it. The crust resists until it fractures. When it fractures, the energy stored in the field releases. It is similar to the way tectonic plates on Earth hold stress until an earthquake. But the scale and the forces are much greater. A magnetar quake releases more energy in a fraction of a second than the sun emits in days. If we imagine approaching a magnetar, the experience would not resemble anything familiar. Long before reaching its surface, the magnetic field would begin to affect instruments. Electronics would fail. Atomic structure itself would change. Light would behave differently. Directions would lose meaning because space would be shaped by the field lines rather than by geometry alone. There would be no safe distance at which to observe directly with ordinary tools. Observations rely on measuring radiation the magnetar emits, not on physical probes. Magnetars rotate, although they often spin more slowly than some neutron stars known as pulsars. The rotation interacts with the magnetic field, producing beams of radiation. If the beams cross Earth, we detect pulses. These pulses can be steady for long periods, but magnetars can also change behavior. Their pulses can shift, their rotation can slow or speed up in small jumps, known as glitches. These glitches suggest that the interior of a magnetar is not static. Neutrons inside may flow in superfluid form. The crust and the core may move relative to each other. The interior of a magnetar is one of the most extreme physical environments theorized. Matter is compressed beyond normal atomic structure. Protons and electrons are forced into neutron-rich states. The density is so high that gravity and quantum forces balance each other. If the mass were slightly higher, gravity would win and the object would collapse into a black hole. A magnetar sits near that threshold, held stable only by the behaviors of nuclear matter. The magnetic field outside a magnetar influences events far from its surface. Fields that strong can trap plasma in loops. The loops can stretch and snap, releasing bursts. Radiation can scatter in ways that change polarization. When astronomers measure the polarization of light from magnetars, they learn how the field shapes space. There is also evidence that magnetars play a role in fast radio bursts, short flashes of radio energy from distant galaxies. Some of these bursts repeat, some occur once. Their exact origin remains uncertain, but magnetars are strong candidates. A sudden shift in magnetic structure could produce a radio burst. If that is correct, magnetars influence signals we detect across billions of light years. Magnetars do not last in their extreme form forever. Over time, the magnetic field decays. The decay releases heat. The surface cools slowly. The object becomes a more ordinary neutron star. But the magnetic decay can take tens of thousands of years. In cosmic terms, that is a short time. Most magnetars we detect are young. They formed recently, often in regions where massive stars are common. The magnetic heart of the void is not empty. It is filled with forces that reshape matter, space, and energy. A magnetar stands as a boundary condition for physical law. It does not break the rules of physics. It shows what happens when the rules operate under pressure far beyond everyday conditions. Where the magnetic field is so strong that atoms lose shape, space bends without gravity, and radiation behaves in ways that defy ordinary experience. In some parts of the universe, there are stars that rotate so fast and so smoothly that their motion seems to defy the weight of the matter they are made of. These stars are millisecond pulsars. They are neutron stars, the compact remains of massive stars that exploded as supernovae. A neutron star packs the mass of a sun into a sphere the size of a city. The density is so high that atoms cannot remain in normal form. Electrons and protons merge into neutrons. The structure becomes a compressed sea of nuclear matter. A neutron star can rotate many times per second. Some rotate hundreds of times per second. The fastest known rotates over 700 times each second. That means a full rotation in less than the blink of an eye. Yet the rotation is not chaotic. It is steady. It does not slow quickly. It does not wobble. It maintains its rotation with a steadiness that rivals the best mechanical clocks humans have built. This is why pulsars, including millisecond pulsars, are sometimes described as cosmic clocks. The reason millisecond pulsars rotate so fast has to do with how they gain rotational speed. After a neutron star forms, it might spin at a normal rate. Over time, it can slow. If the neutron star is in a binary system with another star, matter from the companion can fall onto the neutron star. As the matter falls, it transfers angular momentum. This causes the neutron star to spin faster. The process is called spin up. The neutron star becomes a millisecond pulsar. The fast rotation of the star creates strong magnetic fields. These fields accelerate charged particles and produce beams of radiation that extend from the magnetic poles. As the star rotates, the beams sweep across space. If the beam crosses Earth, we detect pulses of radiation. Each pulse corresponds to one rotation. The pulses are so regular that they can be used to track the passage of time with precision. The timing can be so precise that millisecond pulsars have been used to test theories of gravity. If something disturbs the timing of the pulses, astronomers can detect the disturbance. For example, if the pulsar is in a binary orbit with another neutron star, the orbit causes changes in the pulse timing. Tracking these variations allows scientists to calculate the properties of the system. The behavior of millisecond pulsars has confirmed predictions of general relativity, including the idea that massive orbiting objects radiate gravitational waves and lose orbital energy over time. The smoothness of the rotation is surprising when we consider the forces inside a neutron star. The interior may contain superfluid matter. Superfluids can rotate without friction. In a neutron star, the rotation may be stored in quantized vortices, structures that allow the superfluid to carry angular momentum. The crust of the neutron star may shift slightly while the interior continues rotating with little resistance. The star's rotation is not like the rotation of a solid sphere. It is a coordinated motion of dense nuclear matter and magnetic structure. Sometimes the smooth rotation changes. The star experiences what is called a glitch. A glitch is a sudden change in the rotational period. It may speed up slightly. The change is small but measurable. The glitch suggests that the interior of the star shifted. One idea is that the crust cracked, releasing stored rotational energy. The glitch shows that the interior is dynamic. The whisper-like steadiness is not a sign of simplicity. It is a result of internal balance. To imagine the scale of this motion, consider a spinning ice skater. When the skater pulls in their arms, they spin faster. Angular momentum is conserved. In a neutron star, the same principle applies. The collapse of the star compressed matter inward. The rotation increased. The difference is that the neutron star continued refining its rotation through interactions with other stars and through internal adjustments. The radiation from a millisecond pulsar does not appear as smooth light. It appears as pulses because of the beam structure, but the rotation that produces the pulses is smooth. If we could watch the star's surface rotate, it would move too fast to follow. The surface would spin dozens or hundreds of times before we could process a single second. The magnetic field of a millisecond pulsar also contributes to its behavior. The field may align off-center from the rotation axis. This misalignment produces the sweeping beam effect. The radiation is not visible in the same way as starlight. It is usually detected in radio frequencies. Some pulsars emit X-rays or gamma rays. The emission depends on how particles accelerate around the magnetic field. If someone could approach a millisecond pulsar, the environment would be extreme. The gravity near the surface would be strong enough to crush matter into new forms. The magnetic field would distort atomic structure. Light paths would curve because of gravity. Space near the star would not behave like empty space. But from a great distance, the pulsar is a point of repeating signal. The complexity of the object is reduced to a rhythm. The rotation of a millisecond pulsar stays stable for long periods, but the stability is not permanent. Over long timescales, the pulsar will slow. The magnetic field will weaken. The pulses will become less regular. Eventually, the star will fade as a radio source, but during its active phase, the pulsar acts as a record of its past. The rotation reflects the star's formation, collapse, and interactions. We call this rotation graceful because of how little energy it appears to lose compared to the scale of the forces involved. The star spins in a vacuum. There is almost no friction. The rotation persists because nothing is there to stop it. The star's whisper-like motion is not fragile. It is sustained by the extreme density of its matter. If we look up at the sky, we do not see millisecond pulsars with our eyes. They are too small and too dim, but with radio telescopes, we detect their presence. The pulses arrive across long distances. Each pulse is a moment of timing preserved across space. The star spins far away, steady in motion, held in a balance of gravity, magnetic field, and nuclear forces. The whisper is not sound. It is repetition. It is motion carried into silence. In many solar systems, there are planets that orbit so close to their stars that they seem to defy what we understand about heat, gravity, and stability. These worlds are often called hot Jupiters. They are gas giants, similar to Jupiter in mass or size, but they move in tight orbits around their host stars. Some orbit so close that a year on the planet lasts only a few days. The side facing the star is exposed to intense radiation. Temperatures can rise above 1,000 degrees Celsius. Under such conditions, a planet should lose its atmosphere, or its orbit should decay until it falls into the star. Yet some of these planets continue to orbit with surprising stability. A planet forms far from a star if it is a gas giant. The early stages of formation involve gathering gas from the protoplanetary disk. Gas cannot condense into a stable giant planet when it is too close to the star, because the heat prevents the gas from remaining bound. This means that gas giants usually form in cold regions far from the star. The presence of hot Jupiters close to stars suggests that something moved them inward after formation. One possible explanation is orbital migration. A gas giant forms far out, then interacts with the gas and dust in the disk. Those interactions cause the planet to spiral inward. The movement may continue until the planet reaches a stable orbit close to the star. But the movement is not always smooth. The planet may pass through unstable regions. It may disrupt the orbits of smaller planets. The migration can reshape the entire system. Another possibility involves gravitational interactions with other large bodies. If two large planets interact, one can be thrown outward, while the other moves inward. The inward moving planet may settle into a tight orbit. Sometimes the orbit is highly elliptical, bringing the planet close to the star and then far away. Over time, tidal forces can circularize the orbit. The planet ends up in a stable but extremely close path. But not all planets that move close to their stars survive. Some lose atmosphere, some fall into the star. The survival of certain hot Jupiters raises questions about how they maintain stability. One factor is tidal locking. A planet that orbits close to a star can become tidally locked, meaning the same side always faces the star. This creates a permanent day side and a permanent night side. The day side receives constant heat. The night side remains much cooler. The temperature difference can drive winds across the atmosphere. These winds can move heat from one side to another. The planet does not simply burn, it redistributes energy. The atmosphere of such a planet may also contain molecules that reflect or absorb radiation differently. Some hot Jupiters have reflective cloud layers. These clouds reduce heating by scattering starlight. Others have atmospheres with high-altitude haze that acts as insulation. These factors allow the planet to resist rapid heating. The more puzzling part is why these planets do not fall into the star. When a large object orbits close to a star, tidal forces should transfer angular momentum. The orbit should shrink. Over time, the planet should spiral inward. But some planets maintain their orbits for billions of years. The reason lies in the balance of forces. The planet's orbit may be locked in a stable configuration. The tidal forces may not act strongly enough to change the orbit quickly. The rate of orbital decay may be slower than expected. One example is the planet WASP-12b, a hot Jupiter that orbits very close to its star. It has begun to lose some of its atmosphere. The star is pulling gas from the planet, yet the planet still remains in orbit. It has not fallen into the star. Observations suggest that the orbit is decaying slowly. If the decay continues, the planet may eventually be consumed. But the process takes time, measured in millions of years. During that time, the planet continues its orbit, exposed to intense heat, but still intact. Another example is the planet Kepler-78b. It is a rocky planet, not a gas giant. It orbits its star so closely that its surface is molten, yet it remains in a stable orbit. It should have fallen into the star long ago, according to some models, but it has not. This means our understanding of tidal interactions is incomplete. There may be factors that limit the rate of orbital decay. The composition of the star may influence how energy is transferred. The structure of the planet may influence how it responds to tidal forces. We can think about this using the example of an object spinning on a string. If the string shortens, the object moves faster. But if the object is moving in a way that balances the tension, motion can continue. In the case of a planet, the tension is gravity. The balance involves rotation, orbit, and energy exchange. The planet finds a path that remains stable. Some hot Jupiters show evidence of internal heating. The tidal forces stretch and compress the planet. This creates heat inside. The heat can change the atmosphere. It can produce winds or storms that distribute temperature. The planet does not simply heat from the outside. It also heats from internal forces. This internal heat can keep the structure flexible enough to maintain shape under strong gravity. There are also planets that orbit so close to their stars that they lose mass from the atmosphere, forming long tails of gas. These tails stretch behind the planet like a comet. Yet even with mass loss, the planet remains in orbit. The mass loss does not always lead to instability. In some cases, losing mass reduces tidal forces and stabilizes the orbit further. If a person could observe one of these planets up close, they would not find a burning sphere like a ball of fire. They would see a world where physics balances forces at extreme levels. The day side might glow with heat. The night side might be dark and cooler. Winds might move faster than sound. The atmosphere might shimmer with particles that reflect light. The planet that should have fallen does not survive because of a single factor. It survives because of a balance of forces that hold it in orbit. Gravity does not act alone. Heat, rotation, internal structure, and atmospheric behavior work together. The orbit remains stable, even though it lies close to a region where gravity and radiation are intense. It is a reminder that stability in the universe is not always simple. It can exist under conditions that appear extreme when seen from afar. Most of what we see in images of the universe is light. Stars shine. Galaxies glow in spirals and clusters. Nebulae spread in clouds of color. These images suggest that the universe is full of brightness. But the bright regions are not the majority. The universe is mostly dark space. The darkness between galaxies is wide enough to swallow every point of light many times over. It is not empty in the strict sense. There is matter there. There is radiation. There are fields of energy. But the space is sparse. The density is so low that particles can drift for long distances without interacting. The darkness is not defined by the absence of things. It is defined by the absence of events. To understand the scale of this darkness, consider the distance between galaxies. The Milky Way has about 100,000 light-years of width. The nearest large galaxy, Andromeda, is more than 2 million light-years away. Between the two lies space with almost no stars. There are occasional small galaxies and scattered clouds of hydrogen. But most of the distance is a region where light travels without hitting anything. If someone placed a bright lamp in that space, the lamp would shine into emptiness. The light would continue outward nearly unchanged until it reached a galaxy far away. The darkness is not cold in a simple sense. Temperature of the space between galaxies is set by the cosmic microwave background. That temperature is about 2.7 Kelvin. It is very low, but not absolute zero. It is the remaining warmth of the early universe, stretched across time and expansion. If a grain of dust floated there, it would not freeze in the way water freezes. It would simply exist with little energy. Heat is rare because interactions are rare. Without interactions, temperature has little meaning. Temperature describes the average motion of particles. When there are few particles, average motion becomes difficult to define. Gravity still acts in the darkness. The emptiness is part of the structure of galaxy clusters. Galaxies gather in groups and filaments. Between these filaments lie voids. A void is a region with fewer galaxies. Some voids span hundreds of millions of light years. They are not absolute emptiness. They contain dark matter, which does not emit light. They may contain faint gas, but the density is low enough that the region appears dark in every direction. If we imagine a location in the middle of a void, the night sky would look unfamiliar. There would be no nearby stars. The light of galaxies would appear as small, faint points. The sense of distance would be strong. The silence would not be soundlessness alone. It would be the absence of motion, activity, and structure. The darkness is quiet because nothing nearby interacts. The presence of dark matter in these voids gives them shape. Dark matter forms a framework. Galaxies gather along this framework. Where the framework is sparse, the void appears. The void is not a smooth bubble. It has subtle variations in density. But these variations are small. The void remains dark compared to galaxy clusters. Despite the emptiness, light crosses these voids. Light from distant galaxies travels through them on its way to telescopes on Earth. The light carries information. It tells us how fast the universe expands. It tells us how matter is distributed. When light passes through regions with varying matter, it bends slightly. This bending is called gravitational lensing. By measuring lensing, astronomers infer the presence of dark matter. The void becomes visible not because it emits light, but because it affects light. There is also gas in the darkness. This gas is thin, but it stretches across large distances. The gas is mostly hydrogen. It does not glow under normal conditions. But when a quasar shines through it, the gas leaves patterns in the light. The patterns are called absorption lines. They tell us how the gas is arranged. The darkness between galaxies holds traces of the universe's history. Some theories suggest that the first stars formed in regions like these, not in galaxies. Small pockets of hydrogen may have collapsed under gravity before larger structures formed. These early stars would have lived short lives. Their remains would have dispersed. The darkness may contain the scattered record of those early events. If we think about sound, the darkness is silent because sound needs a medium. Air carries sound on Earth. Water carries sound in the ocean. In the void, there are not enough particles to carry sound. If someone spoke there, the words would not travel. A shout would vanish as soon as it left the mouth. The silence is not the absence of noise. It is the inability for noise to exist. The distance between galaxies also affects how we imagine travel. When science fiction shows ships moving from one galaxy to another, the journey is often presented as quick. In reality, the distance is so large that travel with known physics would take times longer than the age of civilizations. Even light itself takes millions of years to cross these regions. Time acts differently at that scale. Events occur slowly. Change is measured in billions of years. The darkness between galaxies is not hostile. It does not destroy. It simply does not provide. Without radiation, heat, or matter, there is little to sustain complexity. Yet the darkness is part of the universe's structure. It allows galaxies to exist without colliding into one another constantly. It gives scale to the cosmos. The bright regions need the dark regions to be seen. The voids also show that the universe is not uniform. Even though the cosmic microwave background is nearly the same across the sky, matter has gathered in specific places. Gravity pulled matter toward certain regions. These regions became galaxies and clusters. The spaces between remained thin. The darkness is as much a product of gravity as the bright regions of stars. If someone were to look outward from a galaxy, the view would show vast space with faint traces of other galaxies. The contrast creates the sense of isolation that comes with thinking about the universe. The darkness does not end. It stretches as far as light can travel and beyond. It is not a wall. It is a distance that cannot be filled. The space between galaxies reminds us that most of the universe is not lit. What we see is a thin surface compared to the depth of the darkness. The silence is not a lack of activity. It is a state in which activity has no place to occur. Some moons in our solar system produce vibrations that travel through their crusts, oceans, and atmospheres. These vibrations can be measured. They form patterns that resemble tones. The moons do not make sound in the way that musical instruments do. There is no air to carry sound across space, but the vibrations act like sound waves inside the moon's materials. They create movements and resonances that can be detected as shifts in magnetic fields, changes in orbit, or variations in light. These patterns appear as if the moons are singing, even though the song is silent to human ears. One example is Saturn's moon Enceladus. Beneath its icy surface lies an ocean. The ocean does not sit still. It moves under the influence of Saturn's gravity. As the moon orbits Saturn, the gravitational pull stretches and compresses its interior. The movement creates tides inside the ocean. The ocean pushes against the ice shell. The ice shell flexes. The flexing creates vibrations. These vibrations travel through the moon. The moon acts like a resonating body, similar to the way the wooden body of a violin vibrates when strings are bowed. But instead of strings, the driving force is tidal stress. These tidal vibrations can create patterns that repeat at regular intervals. When instruments on board spacecraft measure these intervals, they find frequencies similar to what we would call pitches. The moon does not emit sound, but the vibration pattern can be translated into sound waves we can hear by adjusting frequency. Scientists have done this with data from Cassini, the spacecraft that studied Saturn and its moons. The results sound like long, wavering tones, stable but constantly shifting in color and depth. It is not a melody. It is more like the resonance of an instrument played by pressure rather than touch. Another moon, Jupiter's Io, produces vibrations through volcanic activity. Io is the most volcanically active body in the solar system. The volcanoes on Io erupt because of tidal heating. Jupiter's gravity and the gravity of nearby moons distort Io's interior. The heat generated melts rock. The molten rock moves and breaks through the surface. The eruptions produce pulses that travel through Io's thin crust. These pulses can be tracked as tremors. If converted to audible frequencies, they resemble deep, rough tones, like the rumble of a drum struck from within. Europa, another moon of Jupiter, has an ocean beneath its ice as well. The ice surface has cracks that shift with tidal movement. When the ice moves, it produces low-frequency vibrations that pass through both ice and water. These vibrations can travel for long distances. If a sensor were placed on one of these cracks, it would detect slow, repeating pulses. The pulses would change with Europa's orbit. The moon's song would not be constant. It would rise and fall as it moves closer to and farther from Jupiter. Titan, the largest moon of Saturn, has dense atmosphere and lakes of methane and ethane. The atmosphere allows actual sound to travel. If a person stood on Titan with protective equipment, they could hear wind moving over dunes. But beneath the audible sound, there would be slower, deeper vibrations caused by tides in the methane lakes. These vibrations would be too low to hear. They would be felt more than heard, like the deep hum of distant weather. The idea that moons sing is not metaphor alone. The vibrations are real, physical processes. Each moon is a system. The structure of the moon determines how it vibrates. A thick crust produces different tones than a thin one. A deep ocean produces different patterns than a shallow one. The gravitational relationship with the parent planet shapes the strength and rhythm of tides. In this sense, each moon has a unique resonance. On Earth, seismologists study vibrations inside the planet to understand its interior. They measure how shock waves move through rock. They map the core, mantle, and crust. The same methods apply to moons. By measuring how vibrations travel through a moon, scientists can determine the thickness of layers. They can estimate the depth of oceans. They can learn whether the core is solid or liquid. The song becomes a source of knowledge. Imagine standing on the surface of Enceladus. The ground under you would feel rigid, but not silent. If you placed your hand on the ice, you might feel faint, slow pulses. They would not be strong. They would feel distant, like the memory of motion, rather than motion itself. The pulses would come from deep below, from water pushing against ice, from gravity reshaping the moon moment by moment. In a place with no air, there is no echo. The vibrations do not reverberate in open space. They stay inside the moon. The moon's body carries the movement. Each layer receives the vibration and passes it on. The moon becomes its own resonant cavity. It does not sing out, it sings within. When spacecraft capture data from these moons, they record changes in magnetic fields, gravitational pull, or reflected light. The data is numbers, not sound. But when the numbers are converted to waveforms, the structure of the vibrations appears. The conversion is not artistic, it is direct. It is the same type of conversion used to turn electronic signals into recorded sound. The waves have pitch, they have rhythm, they have timbre, they form something that can be heard. The moons are not aware of their resonance. They do not choose to produce it. They respond to gravity and heat and motion. The singing is the product of mechanical process, but the effect suggests presence. It suggests character. Each moon has a different internal structure and therefore a different set of vibrations. The songs are signatures of identity. The moons that sing remind us that sound is not limited to air. Sound is vibration, and vibration is everywhere matter exists under force. A moon with an ocean under ice can carry vibrations through layers that never see light. A volcanic moon can convert heat and pressure into pulses that travel through rock. A moon with a dense atmosphere can carry vibrations in both solid ground and gas. In every case, the pattern is shaped by orbit, gravity, and interior structure. If humans someday place instruments on these moons, the recordings would not be music in the human sense. They would be patterns of movement, long, slow tones from ocean tides, sharp pulses from volcanic eruptions, whispering surface shifts from crusts pulled by distant gravity. The moons would continue to vibrate whether they are measured or not. Their singing is constant. It exists in silence, held inside forms shaped by forces that act across millions of years. When we look at distant stars and galaxies, we see them as they were, not as they are. Light takes time to travel. A star 100 light years away shows us its past from 100 years ago. A galaxy 1 billion light years away shows us its past from 1 billion years ago. This delay is simple to state, but it leads to situations where the order of events becomes unclear. Sometimes, the light we see began its journey before the object that sent it existed in the form we imagine. The universe allows odd sequences like this because space and time are not fixed backgrounds. They bend, they stretch, they connect events in ways that can appear to run backward. Relativity tells us that time depends on motion and gravity. If an object moves near the speed of light, time for that object slows compared to an outside observer. If light passes near a massive object, its path bends and the time it takes to travel changes. These effects are small in everyday experience. They become noticeable when dealing with stars, galaxies, and black holes. One of the clearest examples appears when light travels around a massive cluster of galaxies. A cluster contains dark matter and many galaxies bound together by gravity. The gravity bends the path of light that passes through or near it. This bending is called gravitational lensing. If a distant galaxy lies behind the cluster can act like a lens and create more than one image of the same galaxy. The images do not arrive at the same time. Each path has a different length. Time passes differently along each path because of the gravity involved. This means one image can show the galaxy at an earlier stage, and another can show it later. To an observer on Earth, both images appear in the sky at once. It looks as though we are seeing the same galaxy at two different ages at the same moment. If something changed in the galaxy, we might see the change in one image and not in the other. In that sense, we would see the older version and the younger version of the galaxy side by side. To describe it casually, the light from the younger version left earlier than the light from the older version. Even though the older state happened first, the order becomes a matter of perspective. Another example involves jets of radiation emitted by supermassive black holes. Some galaxies have black holes at their centers that pull in matter. The matter forms a disk. Magnetic fields in the disk can accelerate charged particles and launch them outward at near light speed. The jets extend far beyond the galaxy. If one jet points toward Earth, the light and radiation from that jet can reach us in a way that makes the jet's motion appear faster than light. This is called superluminal motion. The jet does not break physical laws. Instead, the geometry of the path and the timing make the motion look faster than it is. If matter in the jet emits light at two moments close together, and the jet is moving toward us almost as fast as the light itself, the second signal can arrive very soon after the first. Even if the actual events happened far apart, it can appear as though the second flash happened before the first. The timeline becomes scrambled when viewed from Earth. We see something similar in binary star systems. If two stars orbit closely and one star dies in a supernova, the shock wave moves outward. The explosion emits light. But if gravity bends the light around nearby objects, some paths take longer. We could see the aftershock of the explosion before seeing a precursor event. The sequence is shaped by the routes light takes, not by the order of physical events at the source. Even simple motion can shift time. If two observers move at different speeds, each experiences time differently. If one travels at a speed close to light, time for that traveler slows relative to someone at rest. If that traveler returns, less time has passed for them than for others. This is not a trick of perception. It is physical. Clocks change. Biological processes change. Time itself is flexible. Now imagine a photon emitted from a distant galaxy. Its journey spans billions of years. During that time, the galaxy changes shape. Stars form and die. Black holes move. The light carries the memory of the earlier state. But the galaxy we see now is different. The light left before the current version existed. The light left before the events it represents led to the structure we observe today. If we could travel to that galaxy instantly, we would see something that contradicts what we observe from far away. This idea becomes stronger when considering the early universe. Light from the cosmic microwave background began its journey when the universe first became transparent. The matter that later formed galaxies was still spread thin. The light we see now comes from a state that predates stars, planets, or anything familiar. The light left before the structure of the universe emerged. The light left before the world we know was formed. It shows a past older than the objects we now observe within the same sky. The phrase "light that left before it was born" captures a simple idea. The timelines we infer are not fixed. The universe does not present events in a straight sequence. Motion, gravity and distance stretch and reshape the order in which we see things. The story of the cosmos reaches us with layers of time stacked on one another. We live inside those layers, looking back, not at what is happening, but at what already happened, arranged by the paths light had to take to reach us.